We already know that power system analysis is very important for the GATE exam. So definitely you will get 5 marks from this topic. So that's why careful with the power system analysis part. Okay, now coming to the first topic, which is per unit system. As we already discussed, per unit value means it is the actual value of the quantity divided with the base value of the quantity. So actual value divided with base value is the per unit value. But the first important thing in per unit system is, see, actual value, base value having same units. Okay, so that's why per unit value is unitless. For example, let's say the actual voltage is 10 volts and base voltage is, let's say, 100 volts. If that is the case, what is the per unit value? So V per unit can be written as 10 by what? 100 volts. 10 volts by 100 volts. So volts get cancelled. So that's why per unit value generally unitless. So what are the per unit value here? What is the per unit value here? I can say 0.1 per unit. Okay, that is the per unit voltage. So the first important thing is, so actual value, base value having same units, so per unit value is unitless. And the second thing is, the per unit value may be greater than 1, may be less than 1, or may be equal to 1. Okay, so per unit value may be greater than 1, may be less than 1, may be equal to 1. Don't say that per unit value is always less than 1, that's not correct. Okay, so how to justify this? For example, we have a 100 MVA 11 kV synchronous generator. 100 MVA 11 kV synchronous generator we have. Okay, so this is the generator which is having rating of 11 kV 100 MVA. See, what is the full load current or rated current, which is 100 into 10 power 6 by root 3 into 11 into 10 power 3, we get 5.24 kilo ampere. That is the rated current. Correct or not? The rated current or base current, both are same. S base by root 3 times V line base. So, but the default base is the rating of the machine. That's why I base, if you substitute and you check, you get 5.24 kilo ampere. Now, if I ask the current, what is the full load current? That means if the machine is fully loaded, how much will be the current? Full load current will be same, 5.24 kilo ampere. That means if the machine is operating under rated load, what is the per unit value? The per unit value is 1. Suppose if the machine is operating at 50% of the rated load, think about, then what is the full what is the current, load current? 5.24 by 2 kilo ampere. So that means the per unit value less than 1. Yes, it is possible. Suppose if the machine is delivering a fault current, for example, if there is a 3-phase fault at the generator terminal, if there is a 3-phase fault at the generator terminal, approximately the subtransient fault current is 10 times the full load current. If it is 10 times the full load current, means 52.4 kilo ampere. That means what is the fault current in per unit? That is 10 per unit. That means greater than 1 possible. That's why during fault, generally the per unit value is greater than 1, generally speaking. If the machine is operating less than the rated capacity, if the machine is delivering a load less than the rated capacity, then per unit value less than 1. If the machine is fully loaded, then per unit value is what? Equal to 1. So these are the things we need to understand about the per unit system. So per unit value may be less than 1, may be greater than 1, may be equal to 1 possible. Next, default basis rating of the equipment. Just now we discussed. For example, we have 11 kV 100 MVA generator. 11 kV 100 MVA generator. What is S base? S base means what? It's not complex power base. Careful. It is an apparent power base. The apparent power base is how much? 100 MVA. What is the line voltage base? That is 11 kV. Because the rating of the machine is what? It's 11 kV 100 MVA machine. 11 kV 100 MVA machine means by default, if it has not mentioned, means yes, the voltage base is 11 kV and MVA base is what? 100. That's what we need to understand. That's what the meaning of the note number 3. So the default base is always considered to be the rating of the equipment. Next one is, this is a very important thing, sir. Base value having only magnitude. Phase angle is same for actual value and per unit value. Okay, so if you notice this point, what I am saying is, base value having only magnitude, phase angle is same for actual value and per unit value. So what the meaning is, for example, if I say actual voltage may be something like this, 10 at an angle minus 30 degrees. This is what actual value, because in AC system the actual voltage means it's a complex number which has a magnitude and what? Some phase angle. Okay, correct or not? So the phase angle is what? Minus 30 degrees here. For example, let's say this is volts. Now, if I want to select the base quantity, shall I select like this 100 at an angle minus 30 degrees? This is not correct. The base quantity is always having magnitudes. No phase angle for base quantities. Careful about this. Voltage base 100, maybe 100 at an angle something. That is blender. Okay, so this is not correct. Now I can select the base voltage something like this 100 volts. Yes, that is correct. So that's why what I can say here, what is V per unit? V per unit equal to V actual by V base. If it is V actual by V base, then what I get now? 10 at an angle minus 30 degrees divided with 100. If I solve this, we get 0.1 at an angle minus 30 degrees per unit. So what you can understand from here, the actual value and what? Base value, if you notice, actual value having a magnitude and phase angle, but base value always having magnitude. That's why the phase angle of the per unit value, the phase angle of the actual value, just notice, same. The phase angle of the actual value, phase angle of the per unit value are always same. That is the next important thing in per unit system. Okay, now note number 5, the percentage value equal to per unit value into 100. Okay, for example, let's say V per unit is given to me is 0.5. V per unit is 0.5 per unit. What is percentage V? Let's multiply this 0.5 with 100. Then that gives what? The percentage value. Now tell me what is the percentage value here? 50%. So similarly, if percentage value is given, you can convert back to per unit value. Generally, so the machine data will be given like this. The subtransient, transient and steady state reactances of 11 kV 100 MVA generator are 10%, 50% and 110% respectively. That means percentage values are given, but generally we solve with what? Per unit value. So you divide the percentage value with 100 before doing any calculations, so that we get a per unit value. That is the idea. Okay, so this formula also very important. The next important thing is addition, subtraction, multiplication and division are possible with per unit quantities. That means if you have two per unit numbers, let's say x1 equal to 0.1 per unit, x2 equal to 0.2 per unit. Now I want to calculate the x, that is what? X1 plus x2, that is a relation. Okay, if that is the case, I can directly add the per unit numbers. The resultant is per unit value. Okay, for example, I want to calculate y, that is x1 into x2 into x1 or x1 into x1. Okay, whatever it may be. Then yes, I can do x1 into x2 will give you what? Again y, that is also a per unit number. That means the multiplication, division, addition and subtraction you can directly do on per unit numbers, but you cannot do on what? Percentage numbers. See, strictly speaking, addition and subtraction you can do, possible for what? Percentage numbers, but multiplication and division not possible with what? Percentage quantities. This is what you need to notice. So for understanding this, I am just considering an example. Let's see. So let's say R1 is 50%, R2 is 10%. Now tell me, if R1 and R2, these are the resistances, R1 and R2 are connected in series, R1 and R2 is connected in series, then what is R equivalent? R equivalent is what now? R1 plus R2. So if I directly do this operation on percentage numbers, what I get now? 50 plus 10, 60%. Let's do with per unit numbers. What is R1 per unit? 0.5 per unit. What is R2 per unit? 0.1 per unit. Okay, now tell me, what is R equivalent in per unit? What is R equivalent in per unit? 0.1 plus 0.5, which is 0.6. Now tell me, what is R equivalent in percentage? Just multiplied with 100. So we get what? 60%. What I can say, we can do the addition operation, similarly subtraction also on percentage numbers. Okay, but we cannot do the multiplication and division on percentage numbers. For that I am giving one more example. Let's have a look. For example, let's say the percentage R is given 10 percentage. Percentage I is given, let's say 20 percentage. Now I am asking what is the percentage value of V? Let's do directly. Percentage V equal to percentage I multiplied with percentage R. Suppose if you are doing like this, then what I get? We get 200 percentage. Okay, clear? This is not at all correct. Okay, now have a look. What is V per unit? If I do it in per unit, V per unit is 0.1 into R per unit multiplied with I per unit. I am doing 0.1 multiplied with what? 0.2. That will be 0.02. 0.02. Now tell me what is percentage value after this? Percentage V equal to 0.02 into 100, that is 2 percentage. 0.02 into 100, that is 2 percentage. So from this, what you have understand, or what we can understand is, see, multiplication and division we can do it on what? Per unit quantities, not with percentage quantities. So that's why, sir, whatever may be the mathematical operation, it might be multiplication, division, addition or subtraction, do it with per unit numbers. Later, by multiplying with 100, we can get what? Percentage numbers. Okay, so that is the next important thing in per unit system. Next, have a look. Per unit analysis on single phase system. Okay, so in single phase system, if you want to do the per unit analysis, okay, the first important thing is, basically we have 4 variables, sir. S base means, what is S base? Complex power base or apparent power base? See, complex power means generally, for example, complex power is S. That is, we can write P plus JQ, which has a real part and imaginary part. So, which has a magnitude and what? Phase angle. And phase angle is tan inverse Q by P. Correct or not? This is how we can convert S into what? Polar form. Simple complex number. So, a complex number having a magnitude and phase angle. But the magnitude of the complex number, this is a magnitude. This is called what? Apparent power. Correct or not? Apparent power. So, that is simply magnitude of S. Okay? So, this is called apparent power. See, we know that base quantities always having magnitude, no phase angle for base quantities. That's why when I say S base, that is not complex power base. That is what? Apparent power base, because apparent power not having any phase angle, but complex power having some phase angle. So that's why S base means it is an apparent power base. 100 MVA is the S base. Correct or not? Clear? So we need to say it is what? Apparent power base. Next, so V base, I base and Z base. But careful, while selecting the S base and V base, I base and Z base, these equations should satisfy. These equations should satisfy. For example, let's see, I selected S base is equal to 100 volt ampere, and I selected V base equal to 100 volts, and I base equal to 10 ampere, and Z base equal to, let's say, 10 ohms. Check. See, if I multiply V base and I base, I should get S base. What is V base and I base multiplication? 1000 volt ampere. But what you are selected? 100 volt ampere. Is this correct? No. And V base by Z base is what? I should get 10 ohms. Yes, we are getting 10 ohms. But S base is not satisfied. But tell me, is this the correct way of selection? No. This is not at all correct. You must select the base quantities such that the relations, fundamental relations should satisfy. Okay? Clear? These are the relations for actual quantities and base quantities as well. But careful, in actual quantities, the voltages and currents having some magnitude and phase angle. But when it comes to the base quantities, they are just having only magnitude. Okay? So that's why the point is, so this is not the way of selection. That's why, so to satisfy the fundamental equations, let's fix 2 variables, and the remaining 2 variables you need to calculate. That is the fundamental rule. Okay, what are the 2 variables I am fixing? Apparent power base I am fixing, and also what? Apparent power base I am fixing. Then voltage base I am fixing. Is there any reason to select known base is S base and V base? Very simple, sir. Why I am saying known base is S base and V base is the default rating of any equipment you see, the voltage rating is given and what MVA rating is given. That means if you see the nameplate details of generator or transformer or transmission line, these are the two ratings are available. So many ratings are available, but fundamentally these two ratings are what common for every electrical equipment in power system. What are the two ratings? Apparent power and what voltage rating will be given. For example, let's say 11 kV 100 MVA synchronous machine. There is a synchronous generator whose rating is 11 kV and 100 MVA. So that means, so directly you know the S base, that is 100 MVA, and directly you know the line voltage base, that is what 11 kV. Correct or not? So that's why known base is S base and V base, and unknown base is what Z base and I base. That's what we need to calculate. Okay, but how to calculate I base in terms of S base and V base? We know that I base equal to S base by V base, and Z base is what? Simply V base whole square by S base. That's it. Now similarly, let's see what is V per unit. V actual by V base. What is I per unit? I actual by I base. But what is complex power in per unit? The complex power in per unit, the complex power in per unit is what? S actual by S base. But what is S actual? P actual by J times the Q actual. And S base is okay, fine, it's only magnitude. I can divide like this, PA by S base, J times the QA by S base. Now this is nothing but what? P per unit. Now this is nothing but what? Q per unit. So what you can understand here, there is no concept of P base. For example, P actual is, let's say 50 megawatt. I can't say P base is some 100 megawatt. This is not valid. Only S base is valid. For example, S base is 100 MVA. Now what is P per unit? 50 by 100. That is 0.5 per unit. So that's why the point is clear. There is no concept of P base and Q base. Because when you write P base and Q base means mathematically you need to write P base plus J times the Q base. Correct or not? Suppose you are defining P base and Q base. Think about it. Then you can define S base, P base plus Q base. But S base having what now? Magnitude and phase angle. Is that correct? No. That is why no concept of P base and Q base. Only it is what? S base. And similarly, there is no concept of what? There is no concept of R base and X base. Because if you want to say R per unit is what? R actual by Z base. X per unit is what? X actual by Z base. So that's why the point is clear here. There is no concept of R base. There is no concept of reactance base. Only it is the Z base. Okay. So that's why R base, X base, P base, Q base are not valid. Okay. What is valid? Z bases exist and what? Apparent power bases exist. Okay. Clear? So that is the next important thing in per unit system. Next, per unit analysis of single phase transformer. Okay, this is very simple. We already discussed. The single phase transformer means basically three ratings are given. The primary voltage rating is given, secondary voltage rating is given, and what? Apparent power, which is same for what? Both primary and secondary. So the ratings are considered as default base. Now what is the formula, sir? K equal to transformation ratio is the K that I can define N2 by N1, V2 by V1, I1 by what? I2. The same transformation ratio is also valid for what? Base quantities. But the only difference is maybe this actual voltage is having magnitude and phase angle, but the base voltage is only having magnitude. That you have to notice. Now what is the K now in terms of base? V2 base by V1 base, I1 base by what? I2 base. That means you can write V2 base equal to K times the V1 base. I can write I1 base equal to K times the I2 base, and similarly I can write Z1 base equal to what? Z2 base by K square, and we can write Z2 base equal to Z1 base into what? K square. These formulas are always valid. Okay, because these formulas are valid with the original system, I mean to say actual system, and also valid with what? The base also. Okay, so for a transformer in per unit form, so I'm not going to prove this. Careful. V1 per unit equal to what? V2 per unit. I1 per unit equal to what? I2 per unit. And Z01 per unit equal to what? Z02 per unit, which is equal to Z1 per unit plus Z2 per unit. Now careful here, sir. Z01 means it is the impedance referred to primary. Okay. So I can write like this in actual form. This is the transformer equivalent circuit. See, Z01 is the impedance referred to primary. But what is Z1 and Z2? Z1 and Z2 means I can draw the equivalent circuit like this. This is Z1, this is Z2. This is the primary impedance of the transformer and secondary impedance of the transformer. Okay, that's why nomenclature you should be very careful in the problem. If something is given means you need to understand whether it is Z1 or Z2 or Z01 or Z02. If I want to mention Z01 in the problem means I will clearly say the impedance of the transformer referred to primary. If I want to mention Z02, I will clearly say in the problem saying that the impedance of the transformer referred to secondary. Suppose if I want to say Z1 and Z2, what I will say? The impedance of the transformer of primary, otherwise primary impedance of the transformer, otherwise secondary impedance of the transformer. That's why careful, sir. Okay, but if you add primary impedance in per unit and secondary impedance in per unit, that is equal to Z01 or what? Z02. That means for a single phase transformer, the impedance of the transformer referred to primary, the impedance of the transformer referred to secondary are always same. Similarly, in per unit form, the voltage in primary, the voltage in secondary are always same. And also in per unit form, current in primary and current in secondary are always same. So apart from this, what I can say is, in per unit system, we can define K in per unit form. That is V2 per unit divided with what? V1 per unit. What is this value? Always equal to 1. Okay, K in per unit form, V2 per unit by V1 per unit. Okay, so that's why, so the idea is here, if you want to write a Z01, simple way to prove, Z01 per unit equal to what? Z02 per unit, people will say that by K square, but K must be what? In per unit form, right? In per unit form, this is equal to what? 1. That's why Z01 per unit equal to Z02 per unit. That's why, so when you draw the equivalent circuit of the transformer, we draw like this in actual form. Correct or not? This is Z01 in ohms. This is the equivalent circuit of the transformer referred to primary. Okay. This is in what? Absolute form. Here what? Some transformation ratio K. That means this voltage and this voltage are not equal. Okay. But in per unit form, what I say? Simple equivalent circuit. There is no concept of coupled circuit when you are drawing the equivalent circuit of transformer in per unit form. Coupled circuits are not coming into picture. Why? Because this point and this point having same potential. Because V1 per unit, V2 per unit are same. I can join like that. If the per unit voltages are same, I can join like this in per unit form. So that's why there is no concept of coupled circuits. Okay, when it comes to the transformer equivalent circuit. Okay, that's why the per unit system is very simple. Okay, but in absolute system, what happened? There exists a coupled circuit in transformer equivalent circuit. So that's why the analysis become so bit complex. That's why per unit system is more advantage than absolute system. That's why all the analysis means fault analysis, stability analysis and load flow analysis we carried out in per unit form, not in absolute form. Okay, so that's about the per unit analysis of single phase system. We have seen per unit analysis of transformer as well. Now we will go to the per unit analysis of three phase system. But when it comes to three phase system, there are two variables extra added here. I told you basically four variables: S base, V base, I base and Z base. Okay, S base means fine, right? Z base means fine. Z base means always it's a per phase impedance. Okay. But when I say voltage base, there may be line voltage or there may be phase voltage. If I say current base, there may be a line current and phase current. But line voltage and line voltage and phase voltage, line current and phase currents may be same, may not be same. That depends on the connection what you are dealing. For example, if it is a star connection, line voltage, phase voltage not same. For example, if it is a delta connection, line current and phase currents are not same. That's why better to define all the possible things like S base, line voltage base, phase voltage base, line current base, phase current base, and what? Z base. So these are the things we are going to define now. Have a look here. But it might be star connection or delta connection. These relations are valid. S equal to what? √3 into V line into I line. Careful. This is 3-phase apparent power. This is line voltage magnitude, line current magnitude. Because apparent power means what? You have to select only magnitudes of voltages and currents. Okay. So otherwise you can write 3 into phase voltage magnitude and what? Phase current magnitude. Okay. Now what is Z base? Careful, Z base is always phase voltage by phase current. There is no concept like Z base or Z equal to V line base by I line base. This is a blunder. For star connection or delta connection, this is not valid. Z is always a per phase quantity. You need to define the Z is nothing but phase voltage by phase current. There is no concept like line voltage by line current. Z is always a per phase quantity. Careful about this. Now again the same thing. What are the known bases for us? Yeah, S base and V base are the known base. These are the two known bases for us. Okay, and what are the unknown bases now? What are the unknown base? Unknown is what now? I can write like this. Unknown is what? V phase base is unknown. It might be star connection or delta connection. V phase base is unknown. Then I line base is unknown. I phase base is unknown. And Z base also unknown. Now these are the 4 unknowns. Only 2 knowns. Now let's see if it is a star connection, sir. For a star connection, phase voltage equal to line voltage by √3. Correct or not? But at an angle minus 30. But shall I consider minus 30 now? No. Why? We have deal with only magnitudes here. As I told you already, base quantities having only magnitude. Suppose if it is a 11 kV star connected load. 11 kV star connected load. What is V line base? That's it, 11 kV. What about V phase base? 11 by √3. But don't say 11 by √3 at an angle minus 30. That is not correct. Clear? So the point is we are going to consider only magnitudes. Anyway, fine. What about the line current equal to phase current? Now, what about line current and phase current? They are equal. So that is equal to S base by √3 times V line base. Okay. From this, I line base equal to S base by √3 times V line base. So anyway, I phase base also same. So we are calculated I line base and I phase base in terms of known thing, S base and V line base. Similarly, Z base equal to V phase base and I phase base. Okay. Now if you substitute I phase base and if you substitute V phase base as V line base by √3, V phase base is V line base by √3 here, and I phase base is nothing but what? S base by √3 times V line base, and finally we get Z base equal to V line base whole square by S base. So the Z base is V line base whole square by S base. Careful about that. That is the Z base value for star connection. Now coming to the delta connection here. See here, V phase base and V line base are same. Why? Since it is a delta, phase voltage and line voltage are same. So V phase base equal to V line base. But what about I line base? Yes, S base by √3 times the V line base is what? I line base. Using same formula, because these are the formulas valid for what? Valid for both star and delta connection. Basically we have a star connection or delta connection in power system, in 3-phase system means. Correct or not? Anyway, so these formulas are valid for both star and delta connection. That you have to notice. Okay. And now what is I line base? S base by √3 times V line base. What is I phase base? I phase base is I line base by √3. So I line base by √3 means S base by √3 times the V line base by √3. So that's why we get here 3. S base by 3 times the V line base. Now Z base equal to what now? V phase base by I phase base. Okay, V phase base equal to V line base. Okay, so that's why if I solve, I get here 3. Careful about this. Z base here is 3 into V line base whole square by S base. But here Z base, V line base whole square by S base. Okay. So the simple example here is, for example, have a star connected load. Which is supplied from 11 kV 100 MVA system, and here the resistance is 1 ohm. A star connected load, resistance is 1 ohm, which is supplied from 11 kV 100 MVA system. What is Z star per unit? What is Z star per unit? 1 by V line base 11 square by 100 MVA. Z base, if you, Z base you need to calculate. Z base equal to what now? For star connection, 11 square by what? 100, that is 1.21. So 1.21. Okay, that is for Z star in per unit. Now if I convert this into Z delta, if I convert that into Z delta, so what is Z delta? We get 1 ohm na here. What is delta impedance? Okay, delta impedance will be what? 3 times the star impedance. We get here 3 ohms. All are 3 ohms. Now tell me, what is Z base for delta connection? Z base for delta connection is 3 times KVB base square by MVA base. So how much you get? 3 into 1.21. Now tell me, what is Z delta per unit? Z delta per unit is equal to 3 by 3 into 1.21. That means 1 by 1.21 per unit. So from this, what I can understand, Z star per unit and Z delta per unit are always same. Okay. So that means, if for example, if the question is given, there is a star connected load, the per unit impedance of star connected load is 1 per unit. Now if this star connected load is converted to delta, what is the per unit impedance per phase? Same, 1 per unit only. Careful about this. This is very, very important. That means when you convert star to delta, okay, the per unit impedances will not change. I am saying 3-phase star to 3-phase delta. Okay, when you convert 3-phase star connection to 3-phase delta connection, the per unit impedances will remain same. That you need to accept. Okay, clear? Now we go for the per unit analysis of 3-phase transformer. See, per unit analysis of 3-phase transformer means, the first important thing is, if it is a 3-phase transformer, definitely what is given? The primary line voltage, secondary line voltage, and what? MVA rating. Okay, so transformation ratio is nothing but the phase voltage in the primary by phase voltage in the, phase voltage in the secondary by phase voltage in the primary. Otherwise, phase current by in the primary by phase current in the secondary. So you need to select only phase, not the line. So if I define transformation ratio as V2L by V1L, for example, if I define like this, this is blender. Okay, the transformation ratio is always valid with respect to phase quantities, not valid with respect to line quantities. Okay, now for example, let's say it is a 11 kV by 132 kV transformer. Okay, let's say it is a star delta transformer, for example. Now I am asking to calculate what is the transformation ratio. The transformation ratio that is 132 by 11 by root 3. Okay, 132 by 11 by root 3. Why we have done 132 by 11 by root 3? Very simple. Okay, yeah, 132 by, it is why it is 132 by 11 by root 3? See, in case of secondary voltage, it is delta, na? That's why line voltage and phase voltage are same. Yes, we need to substitute here phase voltage. But 132 kV is the line voltage. But delta, that's why phase voltage is same as line voltage. But star side what? 11 kV is the line voltage, but I want phase voltage, that's why 11 by root 3. Okay, so that's how you need to calculate the transformation ratio. Clear? So these things are also very important here. See, for a transformer, that means for a 3-phase transformer, Next important thing is, for three-phase transformer, if you notice, no matter whether it is star delta or delta star or star star or delta delta, whatever may be the transformer connection, V1 phase, V2 phase always same. Phase voltage in the primary, phase voltage in the secondary always same, and even there is no phase shift. The magnitudes are same and what? Phase angles also same. Okay, clear? Similarly, I1 phase, I2 phase also same. Z01 per unit and Z02 per unit is always same, no matter whether it is star delta, delta star or star star or delta delta connection. But when you see the line voltage in the primary and line voltage in the secondary, see, there exists a phase voltage primary, phase voltage secondary, correct or not? Apart from that, what? Line voltage in the primary, line voltage in the secondary, and also line current in the primary, line current in the secondary. But those relations you should be very careful. See, for star star and delta delta transformer, V1 line and V2 line are same, and I1 line and I2 line also same. Both are in what? Magnitudes and what? Their phase angles. But for a star delta transformer, if you see, star delta transformer, V1 line equal to V2 line at an angle plus 30 degrees. That means there exists a phase shift of what? 30 degrees. So V1 line magnitudes are same, but the phase angle is what? 30 degrees. Similarly, I1 line and I2 line in per unit form are same, but there is a phase shift of what? 30 degrees. Okay. Similarly, delta star transformer, here minus 30 we get. So the idea is simple here. For star star and star delta transformer, for a delta star and star delta transformer, there is a phase shift of 30 degrees, but for a star star and delta delta transformer, so between line quantities there is no phase shift. Clear? So this also very very important about our three-phase transformer in per unit form. Clear? So the next important thing is, this is one simple thing you need to note. If three single phase transformers of each rating V1 by V2, S and X per unit, that means what? It is a transformer, the primary voltage is V1, secondary voltage is V2, MVA rating is S, and its per unit reactance is X per unit. For example, let's say 10% or 10%, nothing but 0.1 per unit. Okay. If I convert this three single phase transformer to form a three phase transformers, that means I have a three single phase transformer, transformer 1 and transformer 2 and transformer 3. I am just making them 3 to form what? A three phase transformer. Three single phase transformers I can reconnect to form a three phase transformer, that I can do. Okay. But if I do like that, MVA rating will be what? 3S. What is the meaning here? If MVA rating of the single phase transformer is, let's say, 10 MVA, then the MVA rating of three phase transformer is what now? 30 MVA. Clear? No matter what is its connection, irrespective of its connection, this is what? True. So irrespective of its connection, these things are true. And what about per unit reactance? Per unit reactance of each single phase transformer is 10%. Now here also same. So that means 10% means in per unit form 0.1 per unit. The per unit reactance will not change. Okay, if I convert three single phase transformer to what? A three phase transformer. But voltage ratings, careful, is based on the connection. Because see, voltage rating for three phase transformer, voltage rating of a three phase transformer is what? Line voltage by line voltage. Correct or not? But single phase transformer by default it is a phase voltage. That you need to accept. Correct or not? So if I say this is what? This is by default phase voltage. By default here phase voltage. But now when I say three phase transformer, you have to show line voltages. Correct or not? And now tell me, if it is star star connection, phase voltage is V1, but line voltage will be root 3 times the V1. So primary voltage rating is root 3 times the V1. Secondary voltage rating is also root 3 times the V1. Now if it is a star delta transformer, yes, primary voltage rating is root 3 V1, but secondary voltage rating is V2. Why? Because phase voltage is V2, line voltage also V2 for delta connection. So based on that logic, we can write the remaining 2. So this is what a very very important thing again. Okay. So please pause the video and you need to write all these formulas. First you need to see the formulas and practice all the formulas. Okay, without seeing what? The board. Okay, I hope you understand. So the revision should be like this. So all the formulas what I am listed here, you have to write again on your notebook. Don't think that your time is wasting. Okay, but you have to write all these formulas. Once you listen this, you need to write all the formulas without looking into the board, and you need to check whether you are written correct or not. So that is how you need to improve yourself. Okay, so I'm going to cover all the formulas which are there in per unit system. Okay, anyway, so the next one, the last formula, yeah, Z per unit new equal to what? Z per unit old into KVB old whole square by KVB new whole square, MVAB new by MVAB old. So what you can understand from here, see, generally we are coming across the changing of base quantities. For example, let's say I have a transformer and generator. See, it is a 11 kV 100 MVA generator which is connected to maybe 13.8 kV by 132 kV transformer of 150 MVA. Now which is per unit impedance 0.1, here per unit impedance is 0.2, for example. See, you have to do the analysis on this network, fault analysis for example. Then you must convert the generator and transformers must be on common base. Common base means, for example, I selected generator rating as base. Okay, if you select generator rating as base, generator per unit reactance will remain same. But what about the transformer per unit reactance will change? The transformer per unit reactance new equal to the old value multiplied with KVB old. Since this generator is on the LV side of the transformer, so you need to see LV side. What is KVB old? Rating of the transformer. So 13.8. What is KVB new? Since we are selected the generator rating as base, 11 whole square. MVAB new is 100. MVAB old is what now? Its rating 150. So this is how we need to convert the reactances onto a common base or impedances onto a common base. Once you done that analysis, then then we can go for any type of analysis. It might be fault or stability or load flow analysis. So when you are doing analysis, the reactances or impedances of all the elements must be converted onto a common base. So for that conversion, this formula playing a very, 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 very important role. Okay, clear? So that's about per unit system. With this, I'm concluding per unit system, and the next topic is symmetrical components. The next topic is symmetrical components. See, the first thing we need to define in symmetrical components is balanced system. Okay, so we come across symmetrical components if system is unbalanced, correct or not? To solve an unbalanced power system in easy way, the symmetrical components are introduced. Suppose if it is a balanced system, I can define VA, VB, VC. What is VA? VA at an angle 0, I can write V. VB is V at an angle minus 120 degrees, I can write alpha square V. Okay, alpha square is 1 at an angle minus 120. And VC is V at an angle plus 120, that is alpha times V. Okay, now apart from that, we can define a parameter alpha. These things are very important, please review. Okay, alpha square and alpha cube is 1, alpha power 4 is alpha, alpha power 5 is alpha square. That means anything power alpha can be written in terms of either 1 or alpha or what? Alpha square. Okay, anything power alpha. Okay, and alpha conjugate is what? Alpha square. Alpha square conjugate is alpha. 1 by alpha, alpha square. 1 by alpha square is alpha. And similarly 1 minus alpha is what? Root 3 at an angle minus 30. Alpha minus 1, root 3 at an angle 150. Similarly, you can review all these terms which are very, very important. Okay, now the next thing is, suppose if it is an unbalanced system. So if it is an unbalanced system, every phasor, it might be voltage phasor or current phasor, can be written sum of positive, negative and zero sequence component. Let's say VA can be written as VA0, VA1 and what? VA2. And VB can be written as VB0, VB1 and VB2, and VC can be written as VC0, VC1 and VC2. But what is the relation here? If it is a positive sequence, the positive sequence consists of how many phasors? 3 phasors, maybe voltage or current. So VA1, VB1 and VC1. Why I am saying it's a positive sequence? Since it is following ABC sequence, that is the original sequence. So a positive sequence consists of 3 phasors equal in magnitude. If you see VA1, VB1, VC1, magnitudes are what? Same. but the phase displacement by 120 degrees. Clear? So VA1 we can written as V1, VB1 we can written as alpha square V1, VC1 we can written as alpha V1. So if we add VA1, VB1 and VC1, that is definitely equal to 0. Similarly, negative sequence means which has a sequence of what now? A, BC or ACB? It's not ABC, sorry, this is ACB sequence. Okay, have a look. ACB sequence, because first A, then C, then B. Clear? So what I can write now? VA2 is V2 at an angle 0, simply V2. VB2 is what? Alpha V2. What about VC2? Alpha square times V2. So VA2 plus VB2 plus VC2 is again 0. And so if you really notice zero sequence again, which has three components, VA0, VB0, VC0, but they are what also called cophasal components, because the phase angle displacement between them is 0. That's what the zero sequence definition. And VA0 plus VB0 plus VC0 is equal to 3 times the VA0. And sometimes he may ask you what is residual voltage. Residual voltage means if you add VA, VB, VC, that is called residual voltage. If I add now, what is VA? This. VA1 plus VB1, VC1 0. VA2 plus VB2 plus VC2 0. And VA0 plus VB0 plus VC0 will be what? 3 times the VA0. The residual voltage is always the zero sequence voltage. Okay? Clear? Because if you add A phase voltage, B phase voltage, C phase voltage, positive sequence voltages sum in all phases will become 0. Negative sequence voltage sum of A and B and C are 0. Just now we have proved VA2, VB2, VC2 0, VA1, VB1, VC1 0. So that's why only VA0, VB0 and VC0, that is not equal to 0. That is VA0, 3 times the VA0. That's for residual voltage, for example, given 300 volts. What is the zero sequence voltage of A phase? 100 volts. Zero sequence voltage of B phase? 100 volts. The zero sequence voltage of C phase also 100 volts. That's what you need to understand. Okay. So, and the next important thing is, see, we can write the relation between the sequence components with what? Unbalanced phasors. The unbalanced phasor is VA, VB, VC. So we can write, okay, VA0, VA1 plus VA2, that is as it is. But what about VB0? Can also written as VA0 plus. What about VB1? Check, VB1 equal to what? Alpha square V1. What about VB2? VB2 is nothing but what? Alpha times VA2, nothing but alpha V2. Similarly, we can write here VC0 also VA0, then alpha VA1. Check, sir, if you have any doubt. What about VC1? Alpha VA1 plus. What about VC2? Alpha square times VA2. Now we can write in matrix form VA, VB, VC. That is equal to, in terms of what? Sequence components. VA0, VB0 and what? Sorry, VA0, yeah, VA0, VA1 and what? VA2. How to write that? See, VA equal to VA0 plus VA1 plus VA2, that's why in the matrix here 1, 1, 1. Correct? Then VB is what? VA0 plus alpha square VA1 plus alpha VA2. VC, VA0 plus alpha VA1 plus alpha square VA2. So this is called unbalanced voltage matrix. Now this is sequence transformation matrix T. Okay, now this is what? Sequence matrix Vs. Unbalanced voltage matrix VP or primary voltage matrix, and this is sequence transformation matrix, and this is the sequence voltage matrix. So what you can understand here, we can write like this: VP equal to T times Vs. Correct or not? Clear? So what I can say, we got VP equal to T times Vs. Correct or not? That's the relation between unbalanced phasors and sequence voltages. So we know what is VP. VP means what? Let me write again here: VA, VB, VC. That is equal to 1 1 1 1 alpha square alpha 1 alpha alpha square times VA naught VA1 VA2. Clear? So now if you want to write VS in terms of VP, so what I can write now? So VS can be written as T inverse times VP. Clear? So that is a relation between sequence voltages and unbalanced phasors. That means VS can be written as T inverse times VP. So what is VS? Again VA naught, VA1, VA2, that is equal to 1 by 3 times T inverse. I am directly writing 1 1 1 1 alpha square, sorry, 1 alpha alpha square 1 alpha square alpha times that's it. But one thing you need to notice here, the expressions for VA naught is what? Directly 1 by 3 VA plus VB plus VC. The expression for VA1 1 by 3 VA plus alpha VB. The expression for VA2 VA plus alpha square VB. That's about VA naught, VA1 and VA2. Okay. So generally in the problem, VA, VB, VC given. For example, if VA, VB, VC given, it may ask you that what are the sequence components of phase A voltage. If the sequence component of phase A voltage means VA naught, VA1 and VA2, you need to calculate. Suppose if the question is calculate the sequence component of all phase voltages, you need to calculate VA naught, VA1, VA2. Then you need to calculate VB naught, VB1, VB2. Then you need to calculate VC naught, VC1 and what? VC2. But you know what is VB naught? VB naught is VA naught. What is VB1? Alpha square VA1. What is VB2? Alpha VA2. Then what is VC naught? Again VA naught. What is VC1? Alpha square, sorry, alpha times VA1. Then what about VC2? That is alpha square times VA2. We already discussed these relations. Okay. So first you need to calculate VA0, VA1, VA2. Later what? We can calculate VB0, VB1, VB2, VC0, VC1, VC2 using simple relation. That means it's just a matter of alpha multiplication. Okay. So that's about the relation between sequence voltages and unbalanced phasor. Similarly you can write for current. Okay. Clear? But one more thing you need to notice here, whatever the sequence transformation matrix we are defined, so that is valid for line voltages and what? Phase voltages, line currents and phase currents. That means, see, the primary voltage matrix, what you are written? T times the VSR. Correct or not? Clear? Suppose if you substitute here line voltages, this is also what? Line value of sequence voltages. If I substitute here phase voltages, this is also what? Phase value of sequence voltages. Okay. Clear, sir? Similarly, this is also correct. IP equal to T times what? IS. So this relation is valid for line quantities. If this is line means this is also line quantities. If this is phase means what? This is also phase quantities. That's what you need to understand. Okay. And I'll give a simple example here. For example, let's say you have a delta connected load. Let's say this is IB, IA. Now what about this IAB, IBC, because this is AB, IAB, IBC, then what? ICA. This is how we can show. Clear? So, what I can write here is, I can write IA0, IA1, IA2. These are what? Tell me. Sequence line currents. Correct or not? Sequence line currents. Okay. That is equal to 1 by 3 times 1, 1, 1, 1 alpha, alpha square, 1 alpha square alpha times unbalanced line currents IA, IB, IC. Okay. These are what? Again line currents. This is valid. Always. Okay. Now, similarly, what I am saying is, we can write IAB0, IAB1, IAB2. What is that? Phase currents. These are called sequence phase currents. Correct or not? They are sequence phase currents. Okay. AB, BC, CA is the phase currents, unbalanced phase currents. Okay. That is equal to 1 by 3 times IAB, IBC, ICA. 1 by 3 times this matrix multiplied with IAB, IBC, ICA. That means whatever the T inverse can be used for what? Converting unbalanced line currents to, converting unbalanced phase currents to sequence phase currents. Converting unbalanced line currents to sequence line currents. Similarly, unbalanced phase voltages to unbalanced sequence phase voltages. Unbalanced line voltages to and sequence phase voltages. At the same time, the sequence transformation matrix also valid for voltage drop. That means this is the sequence voltage drop can be written as T inverse times unbalanced voltage drop delta Vp. So here delta V0, delta V1, delta V2, T inverse matrix you know, then delta Vp means delta Va, delta Vb, delta Vc. That means voltage drop in A phase, B phase, C phase. Okay, clear sir? So the sequence transformation matrix and its inverse is used for what? Line voltages, phase voltages, line currents, phase currents, apart from that voltage drops, but not for powers. Power calculations we cannot use it. Okay, how to do the power calculation I will explain at the end. Okay, so that's it. Now we need to see relation between line and phase quantities in star connected load. Okay, actually by default load is balanced. If you notice, load is always having balanced impedances, but supply may be unbalanced due to some disturbance in the network. Let's say this is the neutral current. Okay, now see what are the phase voltages? Phase voltages I can write like this. The standard way of defining the phase voltages are VA, VB, VC. What about the line voltages? Line voltages VAB. Phase voltage VA means corresponding line voltage is VAB, then VBC, then VCA. Okay, clear? And the next important thing is here, see if you notice one thing, line voltages and phase voltage relation for balanced system we know. For example, for a balanced system, what is line voltage? √3 times phase voltage at an angle plus 30. What about line current? Equal to phase current. This is for balanced system. But now supply is unbalanced. So if supply is unbalanced, positive, negative and zero sequence will coming into picture. Okay. So the simple thing is the positive sequence line voltage equal to, I am not going into the derivation, √3 times the positive sequence phase voltage at an angle plus 30. Because positive sequence having what? Same relation with balanced phasors. Okay. Clear? And the negative sequence line voltage equal to √3 times the negative sequence phase voltage, but at an angle what? Minus 30. And zero sequence line voltage is equal to 0. That means never exist. What I can say? In case of star connection, in the line, the zero sequence component of voltage is always 0. But what about V phase not? May exist. It may 0 or may not be 0. Phase voltage I cannot say, it may exist, but positive and negative sequence voltage definitely exist, but line value of zero sequence voltage is always 0 for star connection. And what about the relation between positive sequence line current and positive sequence phase current? They are equal. IL to I phase 2 equal. IL naught equal to what? I phase naught. Correct or not? IL naught also equal to I phase naught, but careful, it may exist. I cannot say it is definitely exist, it may exist. That's what you need to understand. IL naught equal to I phase naught, it may exist. Okay, clear? And the next important thing here is, sir, suppose if the neutral is ungrounded. Neutral is ungrounded means Zn equal to what? Infinity, something like this. Then definitely this current is 0. Neutral current is 0. But what is the neutral current strictly speaking? IA plus IB plus IC, which is equal to 3 times IA naught. So if neutral is ungrounded, neutral current 0, that means IA naught also 0. So line current and phase current both are what? 0 if the neutral is ungrounded. Suppose if the neutral is grounded, definitely zero sequence current will exist. You can't say like that. It may exist, it may not exist. That depends on the type of unbalance. Okay, clear? That's why careful with the zero sequence. Zero sequence may exist. You can comment on it will never exist when, suppose in this case. And also what? Line value of zero sequence voltage will never exist. Okay, so something like that we can comment. Okay, now that's about the star connection and the relations. Now in case of delta connected load, okay, see, in case of delta connected load, again I am saying line voltage equal to always phase voltage, correct or not? So positive sequence, even what? Negative sequence, even what? Zero sequence. But don't say it will not exist, better to say it may exist. It may exist. Okay, clear? So due to what? Residual voltage, I can say. Next, what about line current positive sequence? Root 3 times phase current positive sequence, just like a balanced relation at an angle minus 30. But what about IL2? Root 3 times I phase 2 at an angle plus 30 degrees. And what about IL naught? Is always 0, but I phase naught may exist. I phase naught may exist, but IL naught is always 0 for delta connected load. For star connected load, VL naught always 0, but V phase naught may exist. So that's about star connected load and delta connected load. And the complex power in terms of symmetrical components. So generally the complex power expression we can write like this: S equal to root 3 S equal to 3 into V phase I phase conjugate. In that, real part is active power and imaginary part is what? Reactive power. But this is only valid for balanced system. Balanced system. If the system is unbalanced, this expression is not valid. So that's why for unbalanced system we have a relation like this. We can write like this: VA, that means every phase separately, VA IA conjugate, VB IB conjugate, similarly VC IC conjugate. In that, real part is total active power of 3 phase, imaginary part is total reactive power is 3 phase. So this is valid for what? Both balanced and unbalanced system. Both balanced and unbalanced system. So VIA conjugate is what? Complex power of A phase, complex power of B phase, complex power of what? C phase. SC, SB. Sometimes he will ask you, what is the active power of A phase for unbalanced case? Okay, VA into IA conjugate. You need to calculate VA, IA, and VA, IA conjugate will give you PA plus JQA. VB, IB conjugate will give you PB plus JQ. And VCIC conjugate will give you PC plus JQ. So if you add them, that is what? Total active power of 3 phase plus J times the total reactive power of 3 phase. Okay, but in terms of symmetrical components, I can write like this: 3 into VA naught IA naught conjugate plus VA1 IA1 conjugate plus VC VA2 IA2 conjugate. In that, real part is active power, imaginary part is reactive power. So these two expressions we can use for unbalanced system depending on what is available. Suppose VA naught, IA naught, VA1, IA1, VA2, IA2 given. Simple way we can draw like this. Instead of calculating VA, IA, VB, IB, VC, IC, that is a lengthy approach. This is a shortcut method. But careful, if voltages and currents are given in per unit, then this 3 will not come. If voltages are currents are given in volt and what amperes, that means volts and amperes, for example, then definitely 3 will come. Okay, careful. This 3 will come only in absolute system. In per unit system, this 3 will not come. I hope you understand this. Okay, 3 multiplication, root 3 multiplication, root 3 division, 3 divisions will not come in per unit system. And one more thing, line voltage in per unit equal to phase voltage in per unit for star connection. Correct or not? Magnitudes are same. Okay, clear? In per unit system, careful, that root 3 factors and 3 factors will not come at all. That's why when you convert star to delta, is the 3 factor came for per unit system? No, it will not come. So that's why, so even for complex power also, when you write for a balanced system, for example, then V phase into what? I phase conjugate. Why V phase into I phase conjugate? This is in what? Per unit. The 3 factor will not come. V phase is per unit, I phase is per unit. So that's why V phase into I phase conjugate is the complex power in per unit for 3 phase. But this 3, why? This is for absolute. By default is absolute. But when you are dealing with the per unit system, you should be very, very careful. Okay. So that's about the symmetrical components. Okay. Now the next important thing is the sequence networks. Now first we need to see sequence networks of star connected load, then sequence networks of delta connected load. Okay, so what are the sequence networks of star connected load? Directly I am writing, sir. See, we have to find out the equivalent positive sequence, equivalent negative sequence and equivalent zero sequence. Okay, clear? But the neutral current is only what? Zero sequence. The neutral potential also what? Representing the zero sequence voltage. Correct or not? So zero sequence voltage, not zero. So that's why neutral reference for positive and negative, because there is no the neutral potential here, positive sequence 0, negative sequence 0. Correct or not? Neutral potential, positive sequence, negative sequence 0, but zero sequence will not be 0. That's why neutral difference for positive sequence, neutral difference for negative sequence, but ground reference for zero sequence. So careful about this. Anyway, the positive sequence equivalent circuit I can write like this. This is what? VA1, this is IA1, and positive sequence impedance Z1. That is nothing but what? Z star only. Okay, tell me, is the neutral is going to influence the positive sequence circuit? No. Neutral impedance? No. Z star, simply. What about negative sequence equivalent circuit? Simple. This is VA2, IA2, this is Z2, that is equal to what? Z star. And what about zero sequence equivalent circuit? Indirectly this is only neutral. Okay, but we get here 2 terms. This is Z0, which is equal to Z star plus 3 Zn. That means this is Z star, this is what? 3 Zn. Now this is IA0 and VA0. But what about this? Ground reference, but not neutral difference. Okay, so from this what I can say, for star connected load, Z1 equal to Z2 equal to Z star, but Z0, Z star plus 3 Zn. That means the neutral connection must be considered for zero sequence equivalent circuit. This is true for generator, transformer, transmission, anything, sir. The zero sequence equivalent circuits, when you are drawing, neutral is the reference, ground is the reference, and neutral impedance will definitely influence. For example, if neutral is solidly grounded, then Z1, Z2 is what? Z star only. They are not going to change. But what about Z0? Simply Z star. So, if the neutral is solidly grounded, positive, negative and zero sequence impedances of star connected load are always same. Okay. Suppose if neutral is ungrounded, what about Z1, Z2? That is equal to Z star only. But what about Z0? Infinity. Why? Because Zn is what? Infinity. But here what? Zn is 0. That's why careful with the neutral grounding information for zero sequence equivalent circuit. Okay. This is true for what? Every equipment of power system. When you are drawing zero sequence equivalent circuit, now you must see the neutral grounding information. Okay. Now next we will move on to the delta connected load. See, for a delta connected load, directly per phase analysis is not possible. So that's why you need to convert that to what? Equivalent star connection. So this is Z delta by 3. But what about the neutral? No concept of zero sequence current, IA0 0. If you show that IA0 0, the neutral must be open. Correct or not? So what is Z1 now? Same. Z2 equal to Z delta by 3. But what about Z0? Infinity for delta correction. Okay. The zero sequence impedance is always infinity for what? Delta connection. Okay. That you need to be very careful. Suppose if it is a synchronous machine. Sequence networks of synchronous machine. See, for sequence networks of synchronous machine, I am considering here a star connected generator with neutral is grounded through an impedance Zn. This is what the three-phase equivalent circuit. Okay, but careful one thing. The positive sequence voltage of generated Eg1 positive, otherwise simply Eg1. Okay, Eg1 equal to simply Eg. But negative sequence component of generated voltage is there na? That is always 0. Because generator is always designed to produce balanced voltages. Whenever balanced voltages are produced, positive sequence only exists. Negative and zero sequence will not exist. Simple common sense. And zero sequence component of generated voltage is always 0. That is the first thing. That's why when you are drawing the positive sequence equivalent circuit, Eg1 is there, voltage is there, voltage available. But negative and zero sequence, the generated voltages are not at all available. So based on this fact, we can draw positive, negative and zero sequence equivalent circuit. Let's see, if I want to draw the positive sequence equivalent circuit of generator, positive sequence. Okay, see how the positive sequence equivalent circuit of the generator, very simple. Let's see, there is a generated voltage, there is a positive sequence impedance, and then let's see, this is IA1, Z1, this is Eg. This is a positive sequence equivalent circuit of generator. Okay, so expression for VA1 is Eg minus IA1 Z1. Tell me, okay, is the neutral impedances came here? No. Positive, negative circuits, equivalent circuit, neutral will not coming into picture. No matter neutral is grounded or ungrounded, network will remain same. Okay, positive sequence equivalent circuit network will remain same. Okay, now let's see here, what is Z1? Careful. Z1 means, you may say this is subtransient reactance, JXD double dash. You can say what? JXD dash. You can say what? JXD. But when we consider XD double dash, if the question is calculate what is subtransient fault current, if the question is calculate the subtransient fault current, then Z1 will be substituted as JXD double dash. If the question is calculate transient fault current, then you have to substitute JXD dash. If the question is sustained fault current or steady state fault current, then you need to substitute JXG. So that means depending on subtransient period, transient period and steady state period, the positive sequence impedance will be changing. Okay, but this is what? Same for salient pole machine and what? Cylindrical rotor. Both salient pole and cylindrical rotor machine, this conclusion is same. But if you really notice, positive sequence current is always going out of the generator, correct or not? But negative and zero sequence current will be coming into the generator, that we will see now. See, yeah, before that, for example, if you draw negative sequence equivalent circuit, what is negative sequence equivalent circuit of generator? Simple. This is IA2, this is Z2, and what about this? VA2. So VA2 is what? IA2 minus IA2 into Z2. That means originally the negative sequence current is going into the generator. If you want to write plus symbol, the original current is what? Into the generator. Because generally VA2 is what? Some value, but inside the generator voltage is not there for negative sequence. Just now we discussed generated voltage for negative sequence is 0. That's why negative sequence current is always going into the generator from the fault location. But positive sequence current is going from generator to fault location. Okay, even zero sequence current also going from fault location to inside the generator. That means negative and positive sequence currents are indirectly flowing in opposite direction, correct or not? And at the fault location, positive sequence voltage is almost 0, but negative and zero sequence voltages are maximum. That's why from there generator negative and zero sequence currents are coming. That means at a fault location, positive sequence voltage is minimum, negative sequence voltage is maximum, zero sequence voltage is maximum. Okay, and at generator location, positive sequence voltage is maximum, but negative and zero sequence voltages are minimum. That's why current is going towards the generator. Okay, anyway, so that's about the negative sequence equivalent circuit. But what is Z2? Irrespective of subtransient period or steady state period or transient period, always XD dash. This is for cylindrical rotor synchronous machine. But salient pole synchronous machine, you need to take what? Average. XD double dash plus XQ double dash by 2. This is for salient pole machine. That means Z2 for cylindrical rotor is always greater than Z2 for salient pole machine. Careful. Okay. But these expressions are same for what? Subtransient, transient or what? Steady state. Don't think that we have substituted here subtransient reactance. That's why this is only for subtransient period, and steady state period I need to take JXD. No. It may be subtransient, transient or steady state. This is what the so formulas. Okay, but one more thing, in case of a negative sequence current flowing in the stator, actually if this is the rotor is rotating in this direction, due to negative sequence current, whatever the magnetic field produced in that is rotating always in the opposite direction to what? Rotor. That means what is the relative speed between them? 2ns. I already discussed, but just remember, negative sequence magnetic field is always rotating in anti-clockwise direction, and rotor is rotating in what? Clockwise direction. That means negative sequence magnetic field and positive sequence magnetic field always rotating in opposite direction, and negative sequence magnetic field, rotor is always rotating in opposite direction. Positive sequence magnetic field and rotor is rotating always in same direction. Okay, clear? Now coming to zero sequence. Now what is zero sequence equivalent circuit? Careful, in case of zero sequence equivalent circuit, you must consider the neutral impedance, but 3 times Zn. Okay, clear? Now this is IA0, and what about this? VA0. Now that VA0 is minus IA0 into ZG0 plus 3 Zn. But what is that ZG0? Just leakage reactance of the generator. Okay, because there is no armature reaction produced by zero sequence current, because in a 3-phase system, if you really notice, for a generator, okay, if there exists a zero sequence current here, IA0, there exists a zero sequence current here, IB0 equal to what? IA0. What about here? IC0 equal to what? IA0. So that's why the rotating magnetic field produced by this zero sequence current is always 0. That means the resultant magnetic field produced by the zero sequence current flowing in stator is 0. If there is no magnetic field, no armature reaction. That's why only leakage reactance is considered for zero sequence. That's why careful, sir. Sum of air gap flux means sum of A phase flux, B phase flux and C phase flux. in the air gap with respect to zero sequence currents is always 0. Negative sequence current there, but rotating opposite direction to the rotor. Positive sequence current is there, rotating in the same direction to the rotor. That's about positive, negative and zero sequence. And careful with the neutral impedance. If neutral is ungrounded, open here. If neutral is solidly grounded, this term is what? 0. Okay. So that's about the sequence networks of what? Synchronous machine. Now we'll see the sequence networks of transmission line. Okay, directly I am saying, sir, for a transmission line, this is the positive sequence equivalent circuit wherever it is connected. Okay, this is the negative sequence equivalent circuit, Z2. Same, equivalent circuits are same. This is the zero sequence equivalent circuit. This is positive, negative and zero sequence equivalent circuit. But what is the Z1? Z1 equal to Zs minus Zm and Z2 equal to Zs minus Zm. And what is Z0? Equal to Zs plus 2Zm plus 3Zn. This is for what? 3-phase 4-wire network. But 3-phase 3-wire network, this Zn is what? 0. Because there is no concept of neutral. Earth is acting as a neutral. Earth resistance is always 0. Clear? So that is the only difference. But what is this Zs self impedance and Zm is what? Mutual impedance. Careful about this. And also I told you about transposer line and untransposer line. Just review that concepts as well apart from this. Okay. Clear? The next one is the sequence networks of transformer. So when it comes to a transformer, okay, the positive and negative sequence networks are same. And moreover, for a transformer, Z1 and Z2 and Z0 is equal to what? J times XL. Leakage reactance only we need to consider. Because there is no concept of armature reaction for generator due to positive or negative or zero sequence. That's why simply equal. Generally this is equal to almost 10%. Okay. Clear? And positive sequence network and negative sequence networks are what? Same. For generator, for transformer, this is Z1. Negative also what? Same, irrespective of its connection. But zero sequence equivalent circuit of transformer, you should be very careful. Okay, so zero sequence equivalent circuit of transformer is really depends on its connection and what? Neutral grounding. Okay, see, if you want to draw the zero sequence equivalent circuit, I can draw using switches. These are series switches and what? Shunt switches. This is what? Z0. Careful. Now this series switch, if it is a star side, series switch is what? Open. Shunt switch also open. SH means shunt switch. If it is star grounded side, series switch close, shunt switch is what? Open. If it is delta side, series switch open, but shunt switch close. Accordingly, we can draw. For example, I want to show star grounded delta. Have a look between two buses, star grounded delta. How it will be? This is the first thing you need to draw. Now, primary side is star grounded, series switch is closed. Shunt switch open, fine. Okay, shunt switch is open now. I can open like this. Done. Secondary is what? Delta. Series switch is what now? Open. But shunt switch is what now? Close. So how to draw that? Let's see. Shunt switch is closed, but series switch is open. Okay, that's how we can draw the zero sequence equivalent circuits of different equipments. Okay, star connected load, delta connected load we have seen, generator we have seen, transformers we have seen. Okay, so for a star connected load, what is Z1, Z2, Z star, and Z0 is what? Z star plus 3Zn. Okay, for delta connected load, Z1 equal to Z2 equal to Z delta by 3, but Z star equal to sorry, Z0 equal to infinity. Okay, for a generator, what happened? Z1 generally greater than Z2 greater than what? Zg0 or simply Z0. Okay, but Z1 equal to Z2 equal to what? Sorry, greater than Zg0. This is for salient pole and this is for cylindrical rotor. Clear? But for transmission line, Z1 equal to Z2, but Z0 is what? Greater than Z1 equal to Z2. Now if you see, approximately Z0 value is 2.5 to 3 times of Z1. 2.5 to 3 times of Z1. Okay. For a transformer, if you notice, Z1 equal to what? Z2 equal to what? Z0. Generally, which is approximately 10%. That's about sequence networks of different equipments. Now after the sequence networks, the next one is sequence diagram. Sequence diagram means very simple, sir. You can draw positive, negative and zero sequence diagram. Okay, for example, I will explain this with an example. If you want to draw the positive sequence diagram, now, just like a reactance diagram, you need to show the generator in series with what? Its impedance, generator impedance. Transformer, simple series impedance. Per unit only we are drawing this. And then transmission line, simple series impedance. And after that, infinite bus. Infinite bus is represented with an voltage source, sir. That's it. Nothing else. Clear? This is what? The positive sequence diagram. And what about negative sequence diagram? Voltage will not be there. Correct or not? So voltage is represented with short circuit. Okay, this is bus 1, bus 2, bus 3 and bus 4 is what? Infinite bus. Positive and negative sequence diagram are very simple. You don't need to see what is transformer connection and what is neutral impedance. Okay, but when it comes to zero sequence diagram, we should be very careful. Since the generator is what? Star connected, neutral is grounded, just ZG0. Suppose if neutral is ungrounded here, for example, then it must be what? Open here. Okay, then after that, transformer primary is what? Delta. Series switch open and shunt switch is what? Close. And then transformer impedance, and primary is what? Star grounded, series switch is closed. Clear? You should be very careful with the transformer. And transmission line is represented with simple series impedance. And after that, after the bus 3, what we have? Star grounded and delta. Star grounded means series switch is closed, and shunt switch here close, and here series switch open. Okay, here shunt switch is open for star grounded side, and this is short. Why that is short? Because infinite bus have represented with voltage source, but zero sequence voltage of infinite bus is always 0. So this is what? The zero sequence diagram. So that's how we can draw the sequence diagram and also calculate driving point impedances for any given. Okay, let's take a short break for 5 minutes. Then we'll start the numerical questions on per unit system and symmetrical components. Okay. Okay, so we'll start the session. See the question on the board. See the question. Yeah, right. So in this question, if you see the per unit active and reactive powers drawn by, the single phase load is given, but the powers are given in what per unit here, if you notice. All right. But the question is what here? First part of the question, if you see, what is the power factor of the load? What is the actual value of apparent power? And what is the actual resistance and reactance of the load? So how to solve this? It's very simple to solve here. Let's see. Look at here. So the per unit complex power we can write. The per unit complex power S per unit equal to what? P per unit plus J times the Q per unit. Yes or no? That is a per unit complex power. P per unit plus J times the Q per unit. So if you calculate, if you substitute, active power is what? 1 per unit and reactive power is what? 0.7 per unit. So then you can calculate the magnitude and phase angle here. 1 plus 0.75 I, right? Now if we convert that into polar form, we get magnitude is 1.25. That is what apparent power in per unit. And the phase angle is what? 36.869 degrees. Now this is nothing but what? The phase angle of the complex power is always called, the power factor angle. We have already studied this. The phase angle of the power factor angle is always called, power factor angle. If this phase angle is positive, then lagging power factor. Phase angle is negative, then leading power factor. So that's why this is nothing but a power factor angle. So if it is power factor angle, what is the power factor? The first question. Cos phi. Cos of that angle, if you substitute, cos phi lag here. Why? I told you, complex power phase angle is positive means the power factor is lagging. The complex power phase angle is negative means the power factor is leading. So using that knowledge, what I can write here? The power factor cos phi lag, that is cos of 36.869. So we get 0.8 lag. That is a power factor. So that is the first part of the question. Now the second part of the question is that what is the actual value of apparent power? Apparent power is what? The per unit. The magnitude of the complex power is called apparent power. This is nothing but what? Apparent power, mod S. Phase angle is what? I told you, power factor angle phi. So what is magnitude of S per unit? This is what we call apparent power. What is that? 1.25. So what is S actual? S actual equal to S per unit times what? S base. S per unit is 1.25. What is S base? The actual value of apparent power means S base is what? 2 kVA means. By default, what is the base voltage here? This is the base voltage, V base. Now by default, the rating is given as what? Base. The rating of the equipment on C considered as what? Default base. So what is S base now? 2. So we get what now? 2.5 kVA. Because this is 2 kVA, right? So 2 kVA into 1.25, we get 2.5. Now, what is the actual resistance and actual reactance? So, how to calculate actual resistance and actual reactance? So, to calculate this, S per unit, we can write this formula is V line square magnitude by Z conjugate. Z conjugate. Z means what? It has resistance and reactance. But what is V line per unit? Actually, the voltage, actual value and base value is same. Always remember, actual voltage is not given, only rated voltage is given, means what? Actual voltage and base voltage is same. And the line voltage in per unit is what now? 1 per unit. So we can write now 1 square by Z conjugate equal to 1 plus J 0.75 per unit. Okay. So if you just find out Z conjugate now, if you do the inverse of this, Z conjugate equal to 0.64 minus 0.48 J 0.48. What is Z now? 0.64 minus plus we get. So from this we can write this is nothing but R per unit, real part. Imaginary part is nothing but X per unit. In the per unit impedance, okay, this is what? The line voltage per unit, again I am saying it is base voltage, actual voltage also same. You have to consider like this. So that's why. So we get the answer is what? 1 per unit is the line voltage. Now if you solve this, but we have to calculate actual resistance and actual reactance. For that, what is Z base? Z base equal to V line base square by S base by default. Clear? But anyway, it's a single phase load. Line voltage and phase voltage are same. There is no concept like line and phase, just V square by Z. And here also, it's just a V base square. Since it is a single phase load, right? So there is no concept like line voltage here. Just V base square by S base. Let's calculate. V base is what? 500 square by 2000. So we get Z base is, 125 ohms. Now what is R actual? R per unit into Z base. So R per unit is how much? 0.64 into 125. We get 80 ohms. X actual. What is X actual? X per unit into Z base. What is X per unit? 0.48. We get 60 ohms. So the actual resistance is 80 ohms and actual reactance is what? 60 ohms. So that's it. We'll move on to the next question. The per unit impedance of a 200 volts by 400 volts single phase 58 transformer is 0.2 per unit and its actual impedance referred to primary is 50 ohms. Calculate the kVA rating of the transformer. See, the actual impedance referred to what given? Z01 given what? Ohms, which is what? 50. But Z01 per unit, Z02 per unit is always same for a single phase transformer. What is that given? 0.2. So now tell me, calculate the kVA rating of the transformer. Let's see, Z01 per unit can be written like this now. Z01 ohms divided with what? Z1 base. Since it is a single phase transformer, what is Z1 base? Z1 base can be written as what? V1 base square by S base. S base. What is V1 base? Let's substitute now. Z01 per unit is 0.2. Z01 ohms. Yes, we know 50. What is V1? Base. Rating is considered as base only. S base we need to calculate now. Okay. So what is S base now? From here. S base equal to 0.2 into 200 square by 50. We'll get 160 volt ampere. Since he's asking kVA, see base, S base is nothing but what? VA rating of transformer. Rating of equipment only we consider as a default base for transformer. Any equipment you take it, the rating only considered as default base. That's what we already discussed. So now tell me, in the question is asking kVA rating, so 0.16 kVA is the answer for the question. 0.16 kVA. I hope this is clear. We'll move on to the next question. See this question. A star and delta connected loads are connected in parallel and supplied from 100 volts 1 kVA mains as shown below. Calculate the per phase per unit impedance. See, when you are calculating the per unit impedance, okay, that means equivalent per unit impedance you have to calculate. First you convert this delta to star. Otherwise, let's calculate the per unit impedance of this separately and this separately. For, Z star is what given? Ohms, 5 ohms. What is Z base? When we are calculating for star connection, Z base is what? V line base square by S base. What is V line base? 100 volts 1 kVA. 100 square by 1000 ohms, which is 10 ohms. So what is Z star per unit? 5. Actual is 5. Base is what? 10. 0.5 per unit. Now similarly, what is Z delta per phase? Ohms. That is given 15 ohms. What is Z base for delta? Is 3 times V line base square by S base. 1 kVA, so 1000. By default, this is the line voltage. This is three-phase apparent power base. Apparent power rating means base. We get 30 ohms. Again, Z delta per unit is what? Actually is 15 by 30. Now when I convert this delta to star, the per unit impedance will remain same. Actual impedance become by 3, but per unit impedance will remain same. So what is now Z equivalent? Z star per unit parallelly combined with what? Z delta per unit. That's it. Nothing wrong. In actual form you have to calculate Z equivalent now. Then what? You have to convert this delta to what? Star. That is what? 5. 5 in parallel. We get what? 2.5. Even you can cross verify at the end. What is Z equivalent actual? If you want, I will write here. Z equivalent in ohms is what? This will be converted to star now. That means by 3. 3 equal impedance connected in delta. If we convert to star, we get by 3. So 5 parallel means 2.5. So equivalent star we converted. Now equivalent star, what is the base impedance? 10 ohms. 2.5 by 10, 0.25. Even here also. 0.5 parallel with what? 0.5. What do you get? 0.25 only. Both the way you are getting the same answer. That means what? When you are converting star to delta, when you are converting delta to star or star to delta for a three-phase system only, the per unit impedances will not change. Okay? Clear? Per unit impedance will not change, but actual impedance will change. Be clarity on this. It's very, very important. Now we'll move on to the next question. The synchronous reactance of a 200 MVA 10 kV 3-phase 58 generator is 1 per unit. So what is its reactance at 100 MVA 20 kV base? So whenever the base voltage changes, what is kVb new here? kVb new, kVb old. It's 10. kVb new is how much? 20. MVAb old means apparent power base 200. MVAb new is 100. Now, what is X per unit new formula? X per unit old. Same formula can be used for R, even for what? Z. Now let's substitute, we will get the answer. What is X per unit old? 1 per unit given. kVb old 10. kVb new 20. MVAb new 100. So here 1 by 4, here 1 by 2, 1 by 8 total. The answer is 0.125 per unit. Now, we'll move on to the next problem. So if you see this question, all right. One is not proper. Okay. Yeah. Two generating units, G1 and G2, or 15 kV. Line with a bus at a midpoint is shown below. G1 250 MVA, 15 kV, positive sequence reactance 25%. G2 also given. L1 and L2, their lengths are what? 10 kilometers. Positive sequence reactance is 0.225 ohms per kilometers. Means what? If you multiply with what? 10, so we can get like this, the equivalent circuit. So indirectly, what is this line 1 reactance? Since it is 10 kilometer and the line 1 and line 2 have identical lines, and indirectly the reactance are 0.225 ohms per kilometer. So if you multiply with 10, we get 2.25 ohms. Here also 2.25 ohms. Now, and generator 1 and generator 2, the ratings are given. So generator 1 is what? 250 MVA. (15 kV), and its positive sequence reactance is 0.25 per unit. Clear? Now here what? Generator 2, 100 MVA. Okay, it's 15 kV again. Then its positive sequence reactance is what? 10% means what? 0.1 per unit. Now, the only thing is you have to change the common base. So for common base, when you are calculating now, it's a 100 MVA common base. So that means this generator reactance will change. KVB old is 15 kV, KVB new also 15 kV, because for complete system KVB new is what? 15 kV. So you don't need to worry about the KVB new, only MVAB. See here, for generator 1, let's say XG1, let me write here, 0.25 is old value. The new value is what? 0.25 into KVB old by KVB new whole square. KVB old and KVB new is what? 15 kV only. So that factor will 1. And MVAB new by MVAB old. MVAB new is 100, MVAB old is what? 250. If I do this, we get 0.1 per unit. Generator 2 is what? Already on 100 MVA base. So that's why this per unit reactance will not change. But what is this? The line 1 and line 2 per unit reactance is what now? The actual value by base value. What is the actual value? 2.25. What is the base value? 15 square by 100. Because V line base square by S base. What is V line base square? KVB square. KVB is 15. MVAB is what? 100. Directly we can do like that. So what I get now? 15 square divided with 100, 2.25. So which will be 1 per unit. Finally, what I can say? The generator reactance, I will draw the impedance diagram now. Generator means what? Voltage source in series with reactance. Otherwise impedance, not a problem. Transmission line, simple series reactance. One more transmission line. Then one more generator. Now this is what? J.1. This is J1. This is J1. This is what? J.1. Okay. This is what? The impedance diagram. Is asking what? Draw the impedance diagram. Positive sequence diagram with the per unit values on 100 MVA common basis. Okay. So this is what? The answer. Clear? This is the impedance diagram for the question. Now we'll move on to the next question. Now let's see this question.
So IA, IB, IC are a set of unbalanced current phasors in a three-phase system. The phase B, zero sequence current IB not given, and phase A current also given, and phase C current also given. Then is asking to calculate what is IB in per unit. IB in per unit. So how to calculate IB in per unit? We know that IA naught equal to what? IB naught equal to what? IC naught. That is equal to, IA plus IB plus IC by 3. So actually IB naught is given, IA given, IC given. Now we need to calculate IB. That's it. What is IB naught? 0.1 at an angle 0 means 0.1. What is IA? 1.1 at an angle 0 means 1.1. Plus IB we don't know. What is IC? 1 at an angle 120 plus 0.1 divided with what? 3. Now let's calculate this IB. What is IB now? IB equal to, okay, here what? 0.3 minus 1.1 minus 0.1 minus 1 at an angle 120. If we do so, what I get? 1.1 So this is 1.2 here. That means what? Minus 0.9 minus 1 at an angle 120 degrees. This is the final answer. But that option is not there. Check. There is no term called 0.9 at an angle 0. So then we can modify this. Let me write like this now. Minus 1 at an angle 120 plus 0.1 I have added here. Why? Because minus 1 plus 0.1 again minus 0.9. Okay, if I take minus common here, 1 plus 120, 1 at an angle 120 plus 0.1. 1 plus 1 at an angle 120 can be written as what? Minus 1 at an angle minus 120. Let me write here, IB. Minus 1 at an angle minus 120 we can write. Plus 0.1 as it is. We are just playing with the quantities to get the correct answer. So what I get now? 0.1 plus 1 at an angle minus 120. Is that option is there? Check. 0.1 plus 1 at an angle 120. Is that option is there? No. Yes. Yeah, 0.1 at an angle 0, 1 at an angle minus 120. So option is what? D. The correct option is what? D. That's how we need to solve. Okay, now we'll move on to the next question. Again, the three identical star connected resistors of 1 per unit are connected to an unbalanced three-phase supply. The load neutral is isolated. The symmetrical components of voltages in per unit are line voltage given. What is the line voltage? VAB1 given. X at an angle theta 1. Then negative sequence line voltage also given, VAB2. Y at an angle theta 2. But both are in what? Per unit. Remember, these are in per unit. Now tell me, he is asking what? If all the per unit calculations are with respect to base values, the phase to neutral sequence voltages are. What is the phase to neutral sequence voltage? VA1 is in per unit is what? He is asking. VA2 per unit is what? He is asking. So what is the relation between line voltage and phase voltage for star connection? Line voltage equal to root 3 times phase voltage at an angle plus 30. But when you are talking in per unit form, root 3 factor will not come. So let me write here. The phase voltage VA1 per unit is VAB1 per unit only but at an angle minus 30. So if I substitute x at an angle theta 1 at an angle minus 30. So we get x at an angle theta 1 minus 30. Now, what about VA2 per unit? VAB2 per unit at an angle plus 30 now. Negative sequence, minus become plus here. These are the formulas. So that's it. X at an angle theta 1 minus 30 and y at an angle theta 2 plus 30. So the option is what? B. Check it. The next question. So in this question, if you see, a three-phase transmission line supplies a delta connected load. The load impedance is Z. The conductor C of the line develops an open circuit fault as shown in the below figure. So that's why IC0 is given. See, open circuit fault at conductor C. So finally IA is there and IB is there. So what is asking? The positive sequence component of line A will be, that means he is asking IA1. You know the formula for IA1? IA1 equal to what? 1 by 3 times IA plus alpha IB plus alpha square IC. So 1 by 3 times. What is IA? 10 at an angle 0 means just write 10. What is IB? 10 at an angle 180 means minus 10. So alpha times minus 10. IC anyway 0. So you take 10 by 3 common. We can write now 1 minus alpha. So what is this 1 minus alpha? 10 by 3. 1 minus alpha is what? Root 3 at an angle minus 30. We know this. We already discussed this. So 10 by root 3 we get at an angle minus 30 degrees. So what is this 10 by root 3? 5.78 at an angle minus 30 degrees amperes. So that's the final answer. So the idea is, if you know the formulas, you can substitute and you will get the answer. It's a directly formula based question. One, you have to know the relation between IA1 with IAIB and IC. IAIB, IC are unbalanced phasors. We have written symmetrical components of current in terms of unbalanced phasors. Okay. Once you know this, things are what? Simple. Clear? Now we'll move on to the next question. Again, this is also similar kind of question where EA, EB, EC are given. Let's see, EA is given 10 at an angle 0, EB given 10 at an angle minus 90, EC given 10 at an angle 120. So what is a positive sequence component of load current is asking. So what is the positive sequence component of load current? To calculate that, I need to calculate here what is IA, what is IB, what is IC. So IA means what? Simply EA by total impedance here J2. Here total impedance is J3. Here total impedance is J4. So IA is what? EA by J2. Total impedance. Yeah. What is EA? 10 at an angle 0. J2. 10 at an angle 0 by J2 means what? 5 at an angle minus 90 degrees ampere. Clear? Now similarly, what is EB? IB. EB by J3. What is EB? 10 at an angle minus 90. That divide with what? J3. We get 3.333 at an angle. Already in the denominator 90 and it comes to the numerator minus 90, so minus 180. Now what about IC? EC by J4. It's an unbalanced system. EC is what? 10 at an angle 120. So 10 by 4 is what? 2.5. J minus 90, 120 minus 90, 30 degrees. Now tell me, what is the positive sequence component IA1? What is the formula for IA1? Just now we written the formula. 1 by 3 times IA plus so 1 by 3 times. IA is what? Directly I am substituting 5 at an angle minus 90 plus alpha IB. Alpha means 1 at an angle 120. 1 at an angle 120, 1 at an angle minus 3.33 at an angle minus 180. Means directly 3.33 at an angle minus 180, 120 degrees is minus 60 plus 30 degrees here. Alpha square means 1 at an angle minus 120. Minus 120 plus 30, again minus 90. Now if I solve this, we get, just try to solve this, try to evaluate this. .5 this is 81.0 actually. Now if you notice, what is the correct answer? Only option D. Nearest answer is that. Okay, we'll move on to the next question. Now, so if you see in this question, the single line diagram of power system is shown below. The driving point zero sequence reactance of bus 3 is clearly mentioned, driving point zero sequence reactance of bus 3. Here is the bus 3. Yes or not? At this bus 3 is asking. Driving point zero sequence reactance of what? Bus 3. So how to calculate the driving point zero sequence reactance? First you have to draw the zero sequence diagram here. If I draw the zero sequence diagram at bus 1, the left side we have a generator and neutral is solidly grounded. This is what? J.1. So reactance only is asking, that's why no need to go with J directly. We can write 0.1 per unit. Yes, transformer primary is delta. Primary delta means what? There is a ground here. Secondary side star grounded with neutral reactance. This is at bus 2. So what is the transformer reactance? 0.15. Neutral reactance will be referred as what? Transformer 0.15. Neutral reactance, how much? 5%. It will be 0.15. 3 times that value will be considered here. So 0.15 again. So total 0.3. But there is a ground here. Now after that there is a transmission line at bus 2. 2 to 5. So what is its reactance? 10%, means 0.1 again. Now this generator is what? Sorry, motor is zero sequence reactance and its neutral is what? Grounded with again some reactance 5%. This is 0.05, but this is 0.05 into 3. Neutral reactance will come 3 times the original value. Clear? Now if you go down from bus 2, primary is star grounded, secondary also star grounded. So directly series switch close both sides. This is bus 3. Now looking from bus 3 is asking. Now again if you go down, transmission line 0.1. Now generator to 0.1, but the neutral is what? Ungrounded here. This is what? Ground. Now if you look from bus 3, assume that if I inject a current here, is that current will come here? No, no current will come here because there is an open circuit to the ground path. No ground path here. So yes, the current will go like this. Current will go like this and current will take a return path here through the ground. Current will also divided here. So that means what? If I look from here, 0.1 series combination with what? The overall impedance here. But this is what? 0.3. This is also 0.3. 0.3, 0.3 are in parallel. Check it here. This side if you go 0.3. This side also if you go 0.15, 0.15. 0.3, 0.3 in parallel. 0.3, 0.3 parallel means 0.15. 0.15 plus 0.1, 0.25. So 0.25 per unit is the answer. Clear? So the current will take this path. Current will take this path. Here it will not go because there is an open circuit here. Because it's a delta connection. You know the sequence networks of transformer already we have seen. So based on that I draw. So the option is what? 0.25 means 25%. Option is A. I think it's clear for you. Now we'll move on to the next question. The per phase impedance of a balanced star connected load is 10 at an angle 30 degree ohms per phase. The neutral of a load is isolated and it is supplied from a 3-phase balanced unbalanced supply. Okay. The positive, negative and zero sequence impedances of the load respectively. So we know already neutral is ungrounded. No? Z1, Z2 is same. What is that? Z star. But what is Z0? Z star plus 3 Zn. Neutral is ungrounded means Zn is what? Infinity. Yes or not? Z1 equal to Z2 equal to Zr, that is 10 at an angle 30 degrees ohms. Neutral ungrounded, Zn is infinity means what? Overall impedance also infinity. So the answer is what? 10 at an angle 30, 10 at an angle 30 and what? Infinity. Clear? Now we will move on to the next question. A balanced star connected load is supplied from a three-phase unbalanced supply. The neutral of load is solidly grounded. Then, if it is solidly grounded, all the three impedances are what? Same. Z1 equal to Z2 equal to what? Z0 equal to Z star. Now this is given the positive, negative and zero sequence impedance of the load. So you can convert this delta to what? Star. Z1 equal to Z2 equal to what? Z delta by 3. But Z0 means what? Always infinity for star connected load. So what is the answer? 10 by 3 and infinity. 10 by 3, 10 by 3 and infinity is the answer. Direct question, direct question. We'll move on to the next question. A delta connected load per phase impedance of 1 per unit and a star connected load of per phase impedance 0.5 per unit are connected in parallel. The zero sequence impedance per phase of equivalent load is Z star per unit, okay. Z star not per unit is what? 1. Okay, but what about Z delta not per unit? Always infinity. So what is Z equivalent? 1 parallel with infinity will be always 1. 1 parallel with open circuit. So the answer is what? 1. Equivalent, no? Both are connected in parallel. Positive sequence voltage depends on all of these because it is an unbalanced load. For an unbalanced load, the positive sequence voltage depends on positive sequence current, negative sequence current and zero sequence current. In fact, all the sequence currents. Clear? The positive and negative sequence impedance of transmission line are 10 ohms and 10 ohms respectively. The zero sequence impedance of transmission line is, you might have studied, zero sequence impedance is what? 2.52 3 times of what? Z1. So that's what approximately, which is 25 to 30. So the best option is what? 30. The synchronous reactance and armature reaction reactance. Synchronous reactance means XS, which has XL plus XA. Synchronous reactance 0.4 given. Armature reaction reactance 0.3 given. If that is the case, XL is what? 0.1 per unit. What is the zero sequence reactance is asking? Zero sequence reactance is nothing but what? XL only. What is XL? 0.1. Check it. Next. The armature reaction produced by damper winding and field windings are represented with fictitious reactants. Damper winding XDW, field winding XFW. Synchronous reactance and armature reaction reactance means XS given. Actually, this is reverse. The synchronous reactance and armature reaction reactance. One 5 per unit respectively. Calculate the subtransient, transient and steady state. The steady state reactance is nothing but what? XS. So what is leakage reactance from these two? xd equal to xl plus xa. xd is what? 0.2. So from this xl is what? 0.05 per unit. So what is the formula for subtransient reactance? XL plus parallel combination of XA let's substitute, we'll get the answer. You can try it. XA parallel with XFW. So let's try, you'll get the answer. Single line diagram is shown below. The positive sequence driving point impedance of bus 2 is. Since he is asking positive sequence diagram does not depend on winding connection and neutral connection. This is at bus 1, transformer. No matter what is the winding connection and transformer grounded. At bus 2, there is a motor. Now, this is 0.2. This is 0.1. This is 0.3. Now, if you look from here, this side 0.3, this side 0.3. 0.3, 0.3 in parallel. So, we get what? 0.15 per unit. Otherwise, 15%. The answer is what? 15%. 0.3 in parallel. Because it's a positive sequence diagram, does not depend on transformer winding connection and neutral grounding. Careful. I hope this is clear for you. Okay, so now we'll move on to fault analysis.
Here we will see the complete fault analysis. See, basically we have a 4 different types of faults: LG fault, LL fault, LLG fault, and three-phase fault. Three-phase fault means triple L fault and triple LG fault. But one important thing here is, if the system is balanced before the fault, then the analysis of triple L and triple LG faults are same. But before the fault, if the system is unbalanced, then analysis of triple L and triple LG faults are different. That is the first thing you need to be very careful. And the second important thing is, the most severe fault on power system is nothing but three-phase fault. Now, out of this three-phase fault, triple L or triple LG is most severe. Yes, triple LG fault is most severe if the system is unbalanced before the fault. Otherwise, triple L and triple LG faults are having what? Same severity. Correct or not? So, if the question is given, which of the following fault is more severe, means the best option is triple LG fault. If you have what? 2 options. Clear? And the next important thing is the most occurrence fault. The most occurrence fault is LG fault. Okay? The most occurrence fault is LG fault, and least occurrence fault is three-phase fault. Among the three-phase fault, triple LG fault is least occurrence fault. Okay, clear? But one important point is, LG fault is the most severe fault at generator terminal. At generator terminal, if there is a fault, LG fault is more severe compared to what? Three-phase fault. Okay, and one more important thing is, if the neutral of the generator is grounded with very high impedance, then LG fault is not severe. Three-phase fault is more severe. So remember this point. On power system, three-phase fault is more severe. At generator terminal, LG fault is more severe. If the question is given like this, if the neutral of the generator is grounded with very high impedance, then which of the following fault is more severe means you need to go for what? Three-phase fault. And most occurrence fault is LG fault. Least occurrence fault is three-phase fault, and that to what? Triple LG fault. Okay, and analysis of triple L and triple LG faults are same. But if the system is unbalanced before the fault, analysis of triple L fault and triple LG faults are really different. Okay, clear? And the next important thing is, whatever may be the type of fault, we have to find out what is the pre-fault voltage. If you are able to calculate the pre-fault voltage, that's enough. If you are calculated the pre-fault voltage now, then the next step is immediately we can calculate the fault current using simple formulas. But the question is how to calculate the pre-phase fault. 90% of the problems, the pre-fault loading condition is not given. Pre-fault loading condition is not given means what? The system is not loaded before the fault. That is a fundamental assumption. If he has mentioned the pre-fault loading condition, you have to accept it. If the pre-fault loading condition not given, then the system is not loaded before the fault. In that case, the pre-fault voltage is considered to be 1 per unit. Okay, clear? Suppose sometimes what he mention is, he will mention that before the fault, at fault location, the voltage is so and so value. If that is the case, the pre-fault voltage is whatever it is specified. Okay, clear? Sometimes he will mention the pre-fault voltage. Let's consider that also. Clear? So, and the very least cases, he will give the pre-fault loading condition. If the pre-fault loading condition is given, then you must calculate what is the pre-fault voltage at fault location using simple KCL and KVL equations. For example, if the question is given like this, there is a generator and there is a transformer, and after the transformer a load is connected. He will mention that the load is drawing some X megawatt of power at some Y power factor at a terminal voltage of Vg. Okay, that is the pre-fault loading condition is given. But he will mention that maybe the fault is happened at generator terminal. Calculate the fault current or fault current contributed by the generator. In that situation, first what you have to do is, before the fault, what is the voltage? Since here the fault is happened now, that's why before the fault, so since here the fault is happened, before the fault, what is the voltage here you need to calculate. How to calculate? Very simple. Let's draw the equivalent circuit of generator, transformer, and after that what? Load. Clear? This is before the fault, and the terminal voltage of the load is given to you. Okay, and this is a transformer reactance, this is a generator reactance. Now this is nothing but V pre-fault, and let's calculate the load current. Load current you can find out easily using V, T, X and Y. That means the voltage, power in megawatt and Y in power factor you can calculate, and you better to convert everything onto per unit first, later you calculate. Once you calculate that, then what is V pre-fault in this case? Very simple. So Vt plus xt times jxt times, better to say jxt times IL. Now this is the pre-fault voltage will be used for fault calculations. Okay, so that's why, sir, 3 ways. Number 1, pre-fault loading condition is not given, pre-fault voltage is not specified, take it as 1 per unit as pre-fault voltage. Number 2, intentionally to create a confusion, he will mention the pre-fault voltage. Let's accept it. Okay. Number 3, pre-fault loading condition is given something like this, and you can calculate the pre-fault voltage using simple KVL equations. So these are the 3 things you need to understand first. But again I am saying 90% of the problems he will not mention the pre-fault loading condition. He will not mention the pre-fault voltage. So let's take the pre-fault voltage is 1 per unit. Because for every fault, the pre-fault voltage is very, very, very important here. Now we will see the LG fault analysis. See, the assumption is that the before the fault generator is not loaded, before the fault system is already balanced. Now, let's say there is a generator and its neutral is grounded through an impedance called ZL. And at the terminals of the generator, there is a LG fault. See, this is what the three-phase equivalents of the circuit of generator. So by default, LG fault is assumed to be on A phase. Nothing wrong to say R phase. You may say ABC sequence or RYB sequence. Okay. So there is a LG fault on A phase. If there is a fault on A phase means this is the fault current. Now what is the fault current? Equal to IA. Now IB and IC are 0 because before the fault the generator is not at all loaded. So IB 0 and what? IC 0. Now since the fault is on A phase, what is the potential from here to here? That is called VA. That VA is 0. That I have shown here. And VB and VC is not equal to 0. Now if you write the sequence current relation, I am not going into the derivation. So remember this. Sequence current relation is that using this information we can find out the sequence current relation, that is IA0 equal to IA1 equal to IA2 equal to IA by 3. So sequence voltage relation is that since VA equal to 0, VA means what? VA0 plus VA1 plus VA2, that is equal to 0. Now what is the fault current? Fault current equal to IA. From here IA equal to what? 3 times IA1, 3 times IA2, 3 times IA0, that I have written here. See, this is the expression for what? Fault current. Now what is a neutral current? Let's see this neutral current, if you apply the KCL at this node, the incoming current equal to outgoing current. We know that IN equal to IA plus IB plus IC. So that's why neutral current is what? IA plus IB plus IC. Since IB and IC are 0, the neutral current is nothing but IA, that is nothing but fault current. Now what is that fault current? Just now we have written expression, so that I have written again here. So the neutral current is nothing but simply 3IA0, 3IA1 and 3IA2 for LG fault only. So there exists a neutral potential here. Since the current is in this direction, this side is plus and this side is minus, and the neutral potential is simply IN into Zn. So that's I written here, IN into Zn, where IN is nothing but what? Fault current. Okay, so that's why minus IF into Zn. Okay, now we can write the sequence networks. Okay, since IA1, IA2, IA0 are same, I can write this is a positive sequence network, negative sequence network and zero sequence networks of generator. These three are now connected in series. Then only currents are equal. And what is this potential from here to here? VA1. What is this? VA2. What is this? VA0. The idea is very simple here. VA0 plus VA1 plus VA2 are what? Equal to 0. Equal to 0 means you need to represent with short circuit. Now I can calculate IA1, IA2, IA0 from here. Since we have only one voltage, three impedances are in series. So that's why. So I can write the IA1 equal to IA2 equal to IA0. That is equal to simply V pre-fault by Z1 plus Z2 plus ZG0 plus 3Zn. Clear? That is the positive, negative and zero sequence currents. Now we know that the fault current is 3 times the IA1 or 3 times IA2 and 3 times IA0. That's why the final expression for fault current is 3 times V pre-fault divided with Z1 plus Z2 plus ZG0 plus 3Zn. Now careful here, suppose if the neutral of the generator is solidly grounded, then this Zn is what? 0. If the neutral is what? Solidly grounded, something like this. And this Zn equal to, you need to substitute infinity if the neutral is what? Ungrounded. For ungrounded neutral, indirectly the fault current is 0. If you have only one generator, okay, if you have n number of generator, then what you can say, this may not be equal to 0. Why? Because maybe this generator neutral is not grounded. Maybe other generator neutrals are maybe grounded. If all the generator neutrals are ungrounded, so in that case you can say the fault current is 0 for if all the generators are operating in parallel. Okay. So anyway, so for a big power system, how to calculate the fault current means you need to calculate positive sequence diagram, negative sequence diagram and zero sequence diagram. You need to see what is the Thevenin's positive sequence impedance, Thevenin's negative sequence impedance and Thevenin's zero sequence impedance. So in that case, what I get, IA1 equal to IA2 equal to IA0, V pre-fault by Z Thevenin 1, Z Thevenin 2 and simply Z Thevenin not. Okay, clear? For a big power system, suppose if the network is given like this, let's say we have a generator, transformer, transmission line. Okay, so maybe this is at bus 3. At bus 3 there is an LG fault. Okay, maybe the generator neutral is ungrounded, here delta star grounded, something like that. Then you need to draw the positive sequence diagram for this, and Z Thevenin 1 you need to calculate. you need to draw the negative sequence diagram, and Z Thevenin 2, looking into the fault terminal, you need to calculate, and you need to draw the zero sequence diagram, and Z Thevenin not, looking into the fault terminals, you need to calculate. And after that, what is the fault current expression? Same, 3 times V pre-fault divided with what? Z Thevenin 1 plus Z Thevenin 2 plus what? Z Thevenin naught. In that case, there is no concept of 3 times the Zn, because that Zn is already covered when you are calculating Thevenin's zero sequence impedance. Okay, so please notice that. Anyway, so this is the expression for fault current if it is a LG fault. So the very important thing is, for LG fault, all the sequence networks are in series, and also VA1 plus VA2 plus VA0 is equal to 0. That's why there exists a short circuit across this series combination. And after that, we can simply calculate the fault current. Okay, clear? And the next thing is, suppose if ZF is not equal to 0. If ZF is not equal to 0 means, what is VA, IA, IF into ZF? Why? Because if you look back, coming back here, if ZF is not equal to 0 means there exists a ZF here. Now in that case, what is VA, IF into ZF? No, correct or not? Here ZF equal to 0 earlier. Now ZF not equal to 0 means VA equal to IF into ZF. That means with fault impedance effect, what happens? VA equal to IF into ZF. What is the meaning of this? Only voltage relation got changed, but fault current is again what? IA, IB 0, IC 0. That's why the point is, due to fault impedance effect, sequence voltage relation will change, but sequence current relations will never change. So VA equal to IF into ZF. If that is the case, let's come back. If VA equal to IF into ZF means VA0 plus VA1 plus VA2 equal to 3 into IA0 into ZF. So IA0, if we take common, 3 ZF. Okay. So VA1, this is VA1, this is VA2, this is VA0. Correct or not? And if we add VA1 plus VA2 plus VA0, that is equal to what? IA0 into 3 ZF. That is the equation we realized using this circuit. So that means 3 ZF is added extra here. That's why, what is the fault current expression? 3 times the V pre-fault by Z1 plus Z2 plus ZG0 plus 3 Zn plus 3 ZF. Okay, clear? And current relations will not change. That means IA0 equal to IA1 equal to IA2. So if you want the expression for that, simply V pre-fault by Z1, Z2, ZG0 plus 3 Zn. This is what? An extra 3 ZF. Clear? So that's about LG fault analysis. Now we'll move on to LL fault analysis. So let's see if there is an LL fault. We assume that the fault is in between B and C phases. Okay, and the fault is not grounded, since it is a LL fault. If that is the case, what is IA? 0. Boundary conditions I am writing, because the before the fault system is not loaded, IA 0, IF equal to simply what? IB. IF equal to IB, that is nothing but minus IC, and VB equal to VC. So we can write sequence current relations. This is IA0 equal to 0, IA1 equal to minus IA2, and this is a sequence voltage relation. Okay. So IA0 0 means you don't need to consider the zero sequence network. The zero sequence network need not be considered here. But for LG fault, yes, they have to consider, because all the sequence currents exist. But here only what? Positive and negative sequence currents are exist. They are in equal magnitude and phase opposition. Phase displacement of 180 degrees, because IA1 equal to minus IA2. And moreover, IA0 is 0. If we add IA0, IA1, IA2, again you will get what? 0. No doubt, IA 0 na? Let's substitute. IA means IA0 plus IA1 plus IA2. Just look back. IA0 anyway 0. IA1 plus IA2 also equal to 0. Okay. And fault current expression, I am not going into the derivation. Directly I given IF equal to minus J root 3 IA1, otherwise plus J root 3 IA2. And the neutral current is what? IA plus IB plus IC. Just look back. IA anyway 0. IB equal to minus IC. So that's why what? IA plus IB plus IC 0. And even neutral voltage also 0 for LL fault. And LL fault, how many sequence networks are present? Only positive and negative sequence network. There is no concept of here zero sequence network, because the zero sequence current during LL fault is 0. Clear? Now let's see what is the equivalent circuit here. Yeah, this is the pre-fault voltage and series with Z1 and IA1. This is the positive sequence and negative sequence, and VA1 equal to VA2 and IA1 equal to minus IA2. Proved with the help of circuit. That means using that VA1 equal to VA2, IA1 equal to minus IA2, I just realized the sequence networks connection for LL fault. Now this is a sequence network connection. So I can calculate IA1, that is equal to minus IA2. What is that? V pre-fault by Z1 plus Z2. This is a simple network. Voltage is there, Z1 and Z2 are in series. That's why voltage by total impedance will be IA1. That is equal to minus IA2. Now what is the fault current? Minus J root 3 times this IA1. Na? So minus J root 3 times IA1. Clear? Okay. Now for example, if there exists a fault impedance which is not equal to 0, then just go back. Yeah. If there is a fault impedance which is not equal to 0, na, then what happens? This is a VB and this is VC. So what I can write now? VB minus VC equal to IF into ZF if fault impedance is not equal to 0. Okay. So that is what I have written here. VB minus VC equal to IF into ZF. So if I solve this, then finally I will get VA1 equal to VA2. Sorry, VA1 minus VA2 equal to IA1 into ZF. Okay, how to realize that? Very simple. Have a look. This is VA1. Na? Here the potential is VA2. Na? VA1 minus VA2 is what? Here the current is what? IA1. Here the current is what? IA2. I told you just now. Due to fault impedance effect, current relations will remain same. Earlier, what is the current relation? IA1 equal to minus IA2. Now also. But voltage relations will change. Earlier, VA1 equal to VA2. But now, VA1 is not equal to VA2. VA1 minus VA2 equal to IA1 into ZF. So here VA1, here VA2. VA1 minus VA2 is the voltage drop across this, and that is what IA1 into ZF. That means this equation is realized here. And finally, what I can say, the IA1 value and fault current. What is IA1? That is equal to minus IA2, V pre-fault by Z1 plus Z2 plus ZF. Only ZF is added here. But earlier, if you see in LG fault, 3 times the ZF is added. Please careful about the difference. And fault current is minus J root 3 times V pre-fault by Z1 plus Z2 plus ZF. Okay. Now that's about LL fault analysis. Okay. So the first important thing is here the zero sequence current 0 and positive and negative sequence voltages are equal. Some of the sequence currents also equal to 0 because IA0 0, IA1 minus IA2, IA1 equal to minus IA2. That's why. Okay. Clear. So that's about LL fault analysis. Clear. Now we will go for LLG fault. Again at the generator terminal, we assumed that there is an LLG fault. Okay. This is what the LLG fault. Since the fault is grounded here, VB and VC that equal to 0. VB equal to VC, but that is equal to 0. That I can say. And the IA0 here, and fault current is nothing but what? Simple KCL, IB plus IC. Correct or not? That's the boundary conditions I written here. VB equal to VC equal to 0, and fault current is simply IB plus IC, and even IA also here 0. So, correct or not? Now what about sequence current relations? Very simple. IA0 plus IA1 plus IA2 equal to 0. Nothing great about here. Why? Because IA 0, IA means I can write IA0 plus IA1 plus IA2. So that's why IA0 plus IA1 plus IA2 equal to 0. And sequence voltage relations are what? VA0 equal to VA1 equal to VA2. That is equal to VA by 3. Okay, I'm not going into the derivation, but this is what? The sequence voltage relations. Since the 3 voltages are same, that's why 3 sequence networks are connected in parallel. Okay, so positive, negative and 0 sequence networks are connected in parallel for LLG fault. And fault current equal to simply 3 times the IA0. Okay, so this is the fault current, that is equal to what? Indirectly neutral current. Neutral current is what? 3 times the 0 sequence current. That is simple common sense. That's why fault current is nothing but the neutral current. Again I am saying here, fault current is nothing but what? Neutral current, or neutral current is nothing but the fault current, that is equal to 3 times the IA0. And there exists a neutral potential. What is the neutral potential? Again minus IN into Zn, otherwise minus IF into Zn. Clear? Now we will see the sequence networks here. Those 3 sequence networks are connected in parallel. So first using network reduction, we can calculate IA1. For that, these 2 impedances are connected in this and this. Combinations are connected in parallel, that will be in series with Z1. and V pre-fault by the total impedance, if you look from here, will give you IA1. That I written here, V pre-fault by Z1 plus Z2 parallel combination with ZG0 plus 3ZN will give you IA1. Then after that you need to apply the current division rule. Means IA1 you know, opposite impedance. Why we take minus IA1? Because this is the incoming current, these two current must be outgoing. But what happening here? This current fundamentally incoming to the node. That's why minus we need to take. Minus IA1 into Z2, opposite impedance by total impedance, Z2 plus ZG0 plus 3ZN. And what is the expression for fault current? Simply 3 times the IA0. After calculating IA0, you can substitute here, we get the fault current for LLG fault. Okay, but if fault impedance not equal to 0, then what I get now? So VB equal to VC, but that is equal to what? IF into ZF. Okay, but if you really solve this, we get VA0 minus VA1 equal to 3 times IA0 into ZF, otherwise IA0 into 3ZF. So if you notice here, this voltage VA1, this voltage VA2. VA1 and VA2 are same, that's why this voltage you may say VA1 or what? VA2. Here voltage from here to what? Ground. Okay. Now similarly the voltage from here to ground is VA0. So this potential is nothing but VA0. VA0 minus VA1 is what? IA0 into 3ZF. That means 3ZF is what? Included here. That means we realized this equation using this simple 3ZF in the network. Okay. So now we can find out what is IA0, what is IA1 using what? Same rule. Okay. IA1 equal to what now? Very simple. The pre-fault voltage IA1 equal to V pre-fault divided with Z1 plus Z2 parallel with ZG0 plus 3ZN plus 3ZF. Clear? That means just 3ZF is added here. Then after that, using current division, calculate IA0. Then after that, the fault current is what? 3 times the IA0. Earlier also 3 times IA0. Now also 3 times IA0. Okay? I hope you understand. Because due to fault impedance effect, voltage relations will change, but current relations will never change. Please notice that. So that's about LLG fault analysis. Now the last one is 3-phase fault. We already discussed triple L and triple LG fault analysis is same. This is a triple L fault, indirectly this is a triple LG fault. But whatever may be the fault, triple L or triple LG, VA, VB, VC equal to 0. And balanced currents, IA, IB, IC are what? Balanced. And fault current is nothing but you may say IA, IB or what? IC. We can calculate the current flowing in each phase, and that is nothing but the fault current. But the magnitude of the currents are same. For example, IA is 10 kilo ampere you got. IB is what? 10 at an angle minus 120 degrees kilo ampere. IC 10 at an angle plus 120 degree kilo ampere. If I ask fault current, simply you say 10 kilo ampere. So that means IA is our fault current originally. So sequence current relation is that IA0 0, IA2 0, IA1 not equal to 0. Actually fault current equal to IA simply, that is equal to what now? IA1 only. Because IA0, IA1, IA0, IA2 0. IA is nothing but IA0 plus IA1 plus IA2. IA0 0, IA2 0. That's why only thing is IA1. And we get VA0, VA1, VA2 0. Neutral current 0. Because system is balanced and the neutral voltage also 0. And what is the equivalent circuit now? Only positive sequence network exists here. Why? Because since IA2 is 0. Okay, clear? So, and IA0 also 0, only positive sequence network, and that to VA1 0, that's why I represented with short circuit. Now I can calculate what is IA1 and what is fault current, V pre-fault by Z1. If ZF not equal to 0, then the ZF is added here. So what is IA1 now? V pre-fault by Z1 plus ZF, that is nothing but fault current. Now that's about 3-phase fault analysis. Nothing great about the fault analysis. The simple thing is you need to careful with how the sequence networks are connected and what is the fault current expression. Okay, clear? Now if it is a loaded system, so how to calculate the fault current? See, if it is a loaded system, as we already discussed, that you must see pre-fault voltage first. Okay, let me draw the equivalent circuit here. See, this is the fault location. Before the fault, the generator is supplying the power to motor, and is clearly given the motor is drawing a power of P per unit at a power factor of PF at a terminal voltage of VT, that also in per unit, for example. Suppose if that is not given in per unit, actual values are given, let's convert everything onto common base first. For every problem, you have to convert everything onto common base. After converting everything onto common base, let's calculate VT in per unit, P in per unit, and power factor. That is not required to be in per unit. Power factor is 0.8 lagging, that's it. Okay, for example, it will not change whether it is in actual system or per unit system. Okay, so again I am saying first step is convert the entire network onto a common base. Second step is calculate where the load is connected, the terminal voltage will be definitely given, that load terminal voltage in per unit, load drawn active power in per unit, and then also then power factor, that is need not be in per unit, that's a simply factor, so that is as it is. Then after that, let's calculate the load current. How to calculate the load current? So P in per unit, even though it is a three-phase system, per unit is nothing but what? Magnitude of VT, magnitude of IL, and then what? Power factor. After calculating IL here, then you need to calculate IL. After calculating IL, the IL actual is equal to, IL phase are equal to magnitude of IL at an angle plus or minus cos inverse of power factor. If it is a lagging power factor, take minus sign. If it is a leading power factor, take plus sign. So after calculating the load current, the next step is, okay, so there are basically two methods to solve this. I am going to explain only one method, that is the Thevenin's theorem. So using Thevenin's theorem, what we need to do is here. So let's see, I am drawing the equivalent circuit. This is a generator. A voltage source in series with reactance, and after that transformer is represented with simple series reactance, and after that transmission line is represented with simple series reactance, and after that one more transformer, simple series reactance, and after that bus 4, and here the motor is located. Motor is represented with voltage source in series with reactance. This is the equivalent circuit, but where the fault is happened? Here. So this is the point we need to calculate V pre-fault. How? By using what? The terminal voltage here. Terminal voltage is given to you now in per unit, and you know the load current. The load current is what? Since we are converted all these elements onto a common base, and also what? In per unit. That's why in per unit, no matter if you have a transformer, the current flowing through the network is what? Same. Correct or not? In per unit, primary current and secondary current are what? Same. That's why. So let's see, this is what? JXT2. This is XTL. This is simply JXT1, transformer 1 reactance. This is JXG. Now this is JXM. Clear? Understand? Now what is the next step is, let's calculate the pre-fault voltage. What is the pre-fault voltage here? Very simple. V pre-fault equal to terminal voltage plus JXT2 times the load current. So pre-fault voltage is ready. Now after that you have to calculate what is the Z Thevenin. How to calculate the Z Thevenin? See, you have to see from this terminal, by short circuiting the voltage sources, from this terminal what is the total impedance, that is Z Thevenin. What is Z Thevenin, sir? Z Thevenin equal to what? These three are in series, these two are in series, and the combination is in parallel. Let me write that: JXG plus JXT1 plus JXL having a parallel combined with JXT2 plus JXL. Once you are ready with Z Thevenin, then what is the fault current, sir? The fault current equal to simply fault current equal to simply V pre-fault by Z Thevenin, because that is by default 3-phase fault, right? V pre-fault by Z Thevenin. So once you are calculated the pre-fault voltage by Z Thevenin, indirectly it is a subtransient fault current, and moreover you need to substitute here what? Subtransient reactances, generator and motor, because for a generator and motor subtransient reactance, transient and steady state reactance will be different, but transmission line and other elements subtransient and transient and steady state reactance are same. Once you are ready with fault current, okay, if the question is simply calculate the fault current, okay, this is the answer, that's it, nothing else. But sometimes you will ask to calculate what is the fault current contributed by the generator and what is the current contributed by the motor. Motor current contribution and generator current contribution he will ask you. In that case, what you need to do is this fault current must be divided into these two parts. Okay, see what is the generator contribution? Delta Ig double dash equal to, okay, If double dash multiplied with, okay, this current you are calculating, that's why what? Opposite impedance you need to multiply, that means Xt2 plus Xm divided with what? The total reactances, means what? Xg, Xt1, Xt2 plus Xtl plus Xm. Using this you can calculate delta Ig double dash. Okay. Now what is the fault current contributed by the generator? Fault current contributed by the generator is delta Ig double dash plus IL. Load current you have to add, that's only different here. Okay. But what about the fault current contributed by the motor? See, first of all you need to calculate what is the fault current which is coming from this side. That is what delta Im double dash. How to calculate delta Im double dash? Simple, If double dash minus delta Ig double dash. Correct or not? So once you done this, then we can write delta Im double dash minus IL, because the load current you have to subtract for motor. Okay, clear? So that is how you need to calculate, right? If it is a loaded condition. Okay, clear? And the one more concept is fault calculations with DC offset current. Okay, there are simple formulas, I am not going into that, you just go through the formulas, I am not writing the formulas. Fault current with DC offset current. Okay, clear? So you just go through it, but now I will take up this last one, fault calculations using Z bus. Okay, for understanding I am just considering a simple example here. It is a 3-bus system. Okay, only at bus 1 generator is located. These are the transmission lines. So you know that for fault calculations the shunt admittance of transmission lines are neglected. So that means every line having only some series reactance. Resistance also we neglect. Every line is represented something like this, X23. Okay. So using simple procedure you can calculate Y bus and Z bus. But careful, if you add the entries of first row, that will not be equal to 0. Why? Because there is an external reactance or external admittance is there, that's because of generator. So that's why simple logic is, if you add Y bus, if you add any row entries of Y bus, if that is equal to 0 means at that bus there is no generator. For example, first row not equal to 0, generator is connected. Second row, definitely you will get what? If you add equal to 0, 100%, because no generator. Third row if you add also, we will get equal to 0. Clear? Because there is no generator at third bus also. Clear? So, and anyway, we can get Z bus also. After inversing Y bus, we can get Z bus. But anyway, in a given problem, Y bus and Z bus is given to you. And just take an example that the fault is at bus 3 with the fault impedance of ZF. Okay, if that is the case, the first step is the fault current. The fault current equal to the pre-fault voltages are generally assumed to be 1 per unit in this case. Okay, because before the fault system is not loaded, before the fault system is balanced, that's why internal voltage of the generator before the fault, e.g. 1 per unit, and all the bus voltages before the fault also 1 per unit, that you need to notice. And pre-fault voltage 1 per unit na, and that divided with Z33, that means you need to pick this. Z33 you have to pick plus what? ZF, that will give you fault current. After calculating the fault current, this is a one possible question, sir, calculate the fault current. That is very, very, very simple. Then second possible question is, what is the post fault voltages at all the buses? Okay, how to calculate the post fault voltages at all the buses? Very simple, have a look. To calculate the post fault voltages at all the buses, the simple thing is, after calculating the fault current, the second thing is post fault voltages at all the buses. Post fault voltage at all the bus means, for example, V1 post fault you need to calculate V1F, that is equal to V1 pre-fault plus delta V1. What is the delta V1 is? Have a look, V1 of 0 is 1 per unit na? What is delta V1? Delta V1 is nothing but the fault current minus of fault current multiplied with from the Z bus matrix Z13. Since we are calculating at bus 1, that's why 1 came here. Since the fault is happened at what? Bus 3, that's why Z13 you have to consider. Remember the formula. Okay, clear? And you substitute, you will get this. Similarly, what about the post fault voltage at bus 2? V1 of 0 pre-fault voltage minus, tell me, fault current multiplied with what? You are calculating for which bus? Second bus, Z2. Fault is happened at which bus? Third bus. Similarly, what about V3F? Sorry, this is V2 of 0. Na? V3 of 0 minus fault current multiplied with, we are calculating for which bus? Third bus. Fault is happened at which bus? Third bus. That's it. You will get what? The post fault voltages at all the buses. Okay, that is the second thing we need to calculate. The second possible question, what are the post fault voltages at different buses? Okay, then the next step is, he will ask you that what are the currents flowing through different lines? Okay, that means what is the fault current flowing through line 1, line 2, line 3, something like that. Okay, I just given a direction, you can follow any direction you want. Okay, clear? For example, if you want to calculate the current flowing from bus 1 to bus 2, that means the line connected between bus 1 to bus 2. Okay, that is the third calculation. So you need to calculate the fault current flowing from the line connected between bus 1 to bus 2, for example. For that, what you need to do? I12 equal to the post fault voltage of bus 1 minus the post fault voltage of bus 2. We are already done now. Then that divided with what is the impedance of the line connected between 1 and 2. See, how to calculate the impedance of the line connected between 1 and 2? Not from Z bus, not from Z bus. This is from Y bus, from Y bus. How to calculate this from Y bus? Very simple. Let's go to the Y bus. Let's go to the Y bus. Pick the Y12, pick the Y12 and minus it and inverse it. Minus 1 by Y12. Simple. Minus 1 by Y12. Similarly, what is the current flowing from bus 2 to bus 3? For example, 2 to 3. Let's see. Simple logic. V2F minus V3F divide with what? Z23. What is Z23, sir? Z23 equal to minus 1 by capital Y23. You pick Y23 and minus it and inverse it. We get Z23 and substitute, you will get it. And similarly, what is I13? I13 equal to, let me write here, I13 equal to V1F minus V3F post fault voltages by Z13. What is Z13? Which is calculated from Y bus. Let's pick the Y13 and minus it and inverse it. Clear? That's how we can calculate the current flowing through the any lines. Okay? Clear? That is the third calculations from using Y bus and Z bus approach. Okay? So, and the fourth calculation is that calculate the current contributed by the generators which is located at any bus. First of all, you need to identify on what buses the generators are located. For a given system, how to calculate? Very simple. For that, you need to approach the Y bus. Let's add the entries. Since anyway here the picture is given, if we add this which is not equal to 0, that means bus 1 having generator. If we add this, we got 0. So bus 2 not having generator. And if we add this, we got 0, for example. So bus 3 also not having generator. So that means where the generator is located? Only at bus 1. Okay. So that's why. So let's see the equivalent circuit. This is JXD. Clear? And this is what at bus 1 now? The post fault voltage of bus 1. And this is what? IG1. The current contributed by the generator at bus 1. This is what? EG, which is considered to be 1 per unit. Now let's see what is IG1. Very simple. IG1 is the fault current contributed by the generator at bus 1. That is equal to simply EG minus V1F divide with okay JXD. Clear, sir? JXD. So JXD is given means you can directly do it. But if JXD is not given, then how to evaluate for JXD? Again from Y bus. JXD equal to, see, you need to add first row entries Y11 plus Y12 plus what? Y13. And inverse it. That will directly give you JXD value. That means impedance of the generator at what? Bus 1. Impedance of the generator at bus 1. This is nothing but what? Impedance of the generator at bus 1. That method will be used to calculate the fault current contributed by the generator. So these are the 4 calculations we will generally perform. Okay, clear? And one more, the miscellaneous point is here. For example, it is a loaded case. Loaded case. Loaded system. Loaded system means there exists a load current. For example, you have a generator feeding directly a load and the load current is known to you. Okay, but here the LG fault is happened. If there is a LG fault, what is the fault current IFLG? Very simple. 3 times V pre-fault by Z1 plus Z2 plus what? Z0. Z0 is Zg0 plus 3Zn. Okay, that's it. You don't need to consider the load impedance. But what is the fault current contributed by the generator? IFLG, simple, plus what? IL, nothing else. Everything will same. Okay, but careful, sometimes he will ask you, what is the positive, negative and zero sequence components of fault current? See, positive sequence current component of fault current equal to negative sequence component of fault current equal to zero sequence component of fault current, that is equal to V pre-fault by Z1 plus Z2 plus what? Z0. Z0 means Zg0 plus 3Zn. Assume. See, this is what? Fault current. That means current flowing in the fault, positive sequence, negative sequence and zero sequence. But he will ask you, what is the positive sequence current contributed by the generator during LG fault? That is equal to whatever may be the positive sequence fault current. Come back. Whatever may be the positive sequence fault current plus load current. Clear? You must add the load current here. But what about the negative sequence current contributed by the generator? Nothing but the negative sequence fault current. Why? Because before the fault system is loaded, fine, but balanced, na? That's why only positive sequence component of load current is there. Negative and zero sequence component of load current will not be there. That's what. And what about the zero sequence component of generator? Zero sequence current contributed by the generator equal to what? Simply zero sequence component of fault current, load current will not be there. That means the load current will be added only to what? Positive sequence, no matter what is the type of fault. Okay, clear? That is a one thing you must Careful. This is, we are not covered actually in the lectures, but careful, sir. So if it is an LG fault, this is the method. Okay. LL fault means same, IA1 you need to add load current, IA2 you don't need to add load current. Okay. So careful about this. Very simple trick, nothing else. Okay. So with this I am concluding fault analysis. Okay. So the first important thing in power system stability is the rotor dynamics. So that means we need to see what is kinetic energy, what is momentum, and what is inertia constant and the relations. Okay. The first very important thing or basic thing is the kinetic energy stored in synchronous machine at synchronous speed. Now this is the formula for kinetic energy stored in synchronous machine, but at what speed? Synchronous speed. So the formula is half into J into omega Sm square into 10 power minus 6 megajoules. You can also say G into H, otherwise half into M into omega S, otherwise 2.31 into 10 power minus 10 WR square product and multiply with N square in megajoules. See, in this case here WR square is what now? See, that is a moment of inertia of the rotor which is given in Lubin feet square. Okay, W indicates weight, that is in lubens, and radius of the rotor in feet. So that's why Lubin feet square. Okay. So if the WR square product is given in Lubin feet square, now we can use this formula directly. You can get the kinetic energy in megajoules. Okay. So but fundamental formula is this, where J is what here? J is the moment of inertia of the rotor in kg meter square. Omega Sm is the synchronous speed in mechanical radians per second. Careful, it's mechanical radians per second. Okay. Now, what is omega Sm? 2 pi ns by 60, where ns is the synchronous speed, that is 120 f by p. Okay. Now, fr is the rated frequency, where p is the number of poles. Now, if you want to calculate the synchronous speed in electrical radians per second, then you must multiply with p by 2, pair of poles. Okay. So, electrical equal to p by 2 times mechanical. So if you solve this by substituting omega Sm equal to 2 pi ns by 60, we get 2 pi f. And one more thing, the m is what here? Momentum, that is in megajoule seconds per electrical radians. This is the m in momentum and megajoule seconds per electrical radians, and g is the MVA rating and h is the inertia constant. You know all these things. G is the MVA rating in MVA, h is the inertia constant in seconds. Otherwise you can say megajoules per MVA, or megawatt second for MVA, or kilowatt second for kVA, watt second for VA, or simply second. All the units are same. That's about the kinetic energy formula. But sometimes he will ask you what is the kinetic energy at 1/5 of synchronous speed, 1/3 of the synchronous speed, whatever it may be. But careful, the kinetic energy is always directly proportional to rotor speed square. If really rotor speed is synchronous speed, then the kinetic energy is also what? At rated value. Rated value means KES. Okay. So depending on the rotor speed, the kinetic energy actually stored in the machine will decrease. But this is the rated kinetic energy, because default the rotor speed is synchronous speed. Clear? So now we will go to the next formula, that is momentum. See, momentum formula is, the first formula is this, J into 2 by P whole square into omega S. Omega S means in electrical radians per second, whose value is 2 pi f. Okay. So the units is megajoule seconds per electrical radian. Otherwise, megajoules can be written as megawatt second. That's why you can get megawatt second square per electrical radians. Now we can have another formula also. We know that the kinetic energy stored is half into m into omega s. So using that we can write m equal to what? M if you keep here 2 times the Ks by omega s. That's what I written here. But Kes means Gh and omega s means 2 pi f, 2 to get cancelled. So this is the very famous formula for momentum, that is Gh by phi f, and megajoule seconds per electrical radians. If you want to write megajoule seconds per electrical degree na, then here you need to substitute what? 180. If you substitute pi as 180, and the units will be megajoule seconds per electrical degree. Should be very careful with the unit, because sometimes he will ask you what is the momentum in megajoule seconds per electrical radians, what is the momentum in megajoule seconds per electrical degree. So based on that, the formula must be taken accordingly. Okay. Now m in per unit form also we can write. M in per unit form means we have to divide with what? Base MVA only. So if you divide with base MVA, Gg get cancelled, we get h by phi f, second square per electrical radian. If you want secant square per electrical degree, that pi must be substituted as 180. So that's about the momentum. These formulas are very, very important, and the units also. Careful about this. Then after that, inertia constant H. See, the inertia constant is defined as the kinetic energy stored at synchronous speed divided with MVA rating. So KES by G, so that's why megajoules for MVA. Megajoules can be written as megawatt second for MVA. If you divide 1000, numerator and denominator value will not change, but the units become kilowatt second per kVA. Otherwise, watt second for VA are simply seconds. Now that's the units for inertia constant. Okay, clear? So basic kinetic energy, momentum, and what? Inertia constant. These are the three things which are very, very important, and the relations also. Instability is swing equation of synchronous machine. The swing equation is basically a non-linear equation, and also it is a second order differential equation, and that explains the rotor dynamics. Okay, now if you notice here, this is the swing equation in mechanical terms, J into d square theta by dt square, that is equal to mechanical torque minus electrical torque, and you know the units, Newton meters. Torque units are Newton meters, where theta is the rotor angular position, is measured in mechanical radians with respect to stationary reference axis. Again I am saying theta is the rotor angular position measured with respect to a stationary reference axis, and this is in mechanical radians. Okay, now theta m is the mechanical torque in Newton meters, theta e is the electrical torque in Newton meters. Accelerating torque, whatever the difference between Tm and Te, that is called accelerating torque. Okay, so that is also in Newton meters. And alpha m is the mechanical acceleration or angular acceleration in mechanical radians per second square. You may say mechanical acceleration. Electrical acceleration is Pa by m. Mechanical acceleration is Ta by J. Anyway, so that is in mechanical radians per second square. Okay, so and in electrical terms we can write the swing equation as, if you notice here, yeah, m d square delta by dt square, that is equal to Pm minus Pe megawatt. If you want to write in per unit, this is the formula in per unit. M in per unit, d square delta by dt square, that is equal to Pm minus Pe, that is in per unit. Otherwise M in per unit is nothing but h by phi f, that's what I substituted here. Okay, now what is Pm minus Pe? That is called accelerating power. This is called accelerating power, and that divided with m will give you acceleration in electrical radians per second square. And acceleration is very, very important here, sir. So let's see, based on the units we can write like this. Alpha is the acceleration, no doubt, electrical acceleration. Pa if you substitute in megawatt na, and m must be substituted as gh by phi f, so the answer will be electrical radians per second square. Suppose if you substitute Pa is in per unit na, then m must be h by phi f, careful, and the units will remain same. Suppose if Pa is in megawatt, and if you substitute gh by 180 f ms, then we get electrical degree per second square. Suppose if Pa is in per unit and m is substituted as h by phi f, and then we can get here, this is h, this is not pi, careful, this is 180. Then we get electrical degree per second square. Okay, now similarly we can write the accelerating torque. Accelerating torque equal to accelerating power divided with synchronous speed in mechanical radians per second. Okay, that gives accelerating power. Okay, and the next important thing is, yeah, before that, suppose if acceleration alpha is maintained constant, if acceleration alpha is maintained constant for t seconds, within this t seconds there is a change in load angle. The formula I am directly giving, sir, 1 by 2 alpha t square. Okay, there is a change in rotor speed, that is alpha by 3p into time. See, these two formulas are valid if acceleration alpha is maintained constant. And one more important thing is the del delta variation with respect to time is non-linear, you may say hyperbola, and change in rotor speed variation with respect to time is, for constant acceleration we get a linear curve, but this is parabola, this is linear. You may say it's a non-linear, and here it is linear. So you can find out the new rotor speed and new load angle. Okay, what is the new load angle? If the acceleration is maintained constant, initial load angle plus delta delta. What is the new rotor speed? If the acceleration is maintained constant for t seconds, ns plus or minus delta n. When we take here plus symbol, if there is a acceleration, and minus symbol if there is a deceleration. Okay, so that's about the first important thing in power system stability. Now second thing is, for generator action, if you see, always the rotor angular position is ahead of synchronously rotating reference frame. This is a stationary reference axis, just for understanding I written here. So from here this is rotating at synchronous speed, that's why initially these two are coincident. With respect to time, the phase angle between these two will be omega sm into t, where theta is the angle which is measured with respect to stationary reference axis. Rotor angular position measured with respect to stationary reference axis, and delta is the rotor angular position with respect to synchronously rotating reference axis, and this is the relation. Okay, clear? Anyway, if mechanical power is greater than electrical power, always accelerating power is positive, rotor is accelerated. In that case, rotor speed will increase. If Pm less than Pe, accelerating power is negative, then definitely rotor is what? Decelerated, and rotor speed is decreasing. And then if Pm equal to Pe, for example, accelerating power is 0 and the rotor is neither accelerated nor decelerated, and the rotor speed is always maintained constant. Okay, clear? And the next one, for example, if rotor speed is greater than synchronous speed, then what happened? If you see these two, this is the rotor angular position and this is synchronously rotating reference frame, both are rotating in anti-clockwise direction. For example, if rotor speed is equal to synchronous speed, this angle is maintained constant. That is the third statement here I written. If rotor speed is synchronous speed, this angle is maintained constant. Suppose if this fellow is rotating with more speed, then what happened? Angle will increase. That's what. If rotor speed is greater than synchronous speed, angle will definitely increase. If rotor speed is less than synchronous speed, an angle will definitely decrease. This is for generator action. For motor action, this is exactly reverse. Because in case of generator action, if you notice here, always rotor angular position is ahead of synchronously rotating reference frame in the direction of rotation. In the direction of rotation, who is going first? Rotor, then later synchronously rotating reference frame. That means the rotor is ahead of synchronously rotating reference frame in the direction of rotation for generator action. But in case of motor action, the rotor is fall back in the direction of rotation. The rotor is rotating in this direction. Okay, synchronously rotating reference frame is rotating first, moving first, then rotor is moving later. That's why what I can say, so rotor is always fall backs the synchronously rotating reference frame for motoring action. Okay, but for motor swing equation is this: md square delta by dt square equal to Pe minus Pm. That Pe minus Pm is called accelerating power. Now for example, if mechanical power is greater than electrical power, accelerating power is negative here, because Pa is Pe minus Pm, and rotor will decelerate and rotor speed will decrease. If mechanical power is less than electrical power, then what? Pa is positive and rotor will be accelerated and rotor speed will increase. For example, if mechanical power equal to electrical power, then what happened? Accelerating power we get 0 and rotor is neither accelerated nor decelerated and rotor speed is maintained constant. For example, if Nr greater than Ns, if Nr greater than Ns, then rotor will be approaching synchronously rotating reference frame. That's why load angle is decreasing. For Nr less than Ns, load angle will increase, and Nr equal to Ns, the load angle is maintained constant. Okay. Now the next important thing is coherent operation and non-coherent operation. But before that, we see multi-machine system. Multi-machine system means if you have more than n machines or more than one machine is running in parallel, then we must convert the swing equation of all the machines onto a common base. That means you must convert on left side of the swing equation and right side of the swing equation onto a common base. See, first of all, we have to convert H onto a common base. How to convert H onto a common base? For example, H machine is given on what? G machine. H is given by considering machine rating as base. Now I want to calculate H system on what base? G system base. For that we have a simple formula. H system, that means the inertia constant on system base, is equal to G machine into H machine by G system. Okay, so like that you can convert every machine inertia constant onto a common base. So that's why, so remember one thing, sir, whenever base MVA changes, whenever base MVA changes, what will change? For example, H will change or not change? H will change. Okay, tick right mark for change, cross mark for no change. Okay, M in actual form, M actual means what? Will not change. M actual means megajoules seconds per electrical radian. It will never change, remain same. Then M in per unit form, M in per unit form definitely will change. M in per unit form means what is the units? Second square per electrical radian. That will definitely change. And next, alpha acceleration, that will never change. So H will change, M in per unit form will change, but M in actual form, alpha will never change if there is a change in base MVA. Careful about this, this is very, very important. And so coherent operation and non-coherent operation. Suppose if two machines are running in parallel, okay, then what is coherent operation and what is non-coherent operation we need to understand. Coherent operation means all the machines are swinging together. Non-coherent operation means if the machines are swinging in opposite directions. For example, generators are running in parallel. It's called what? Coherent operation. Generator and motor running in parallel, that's called what? Non-coherent operation. For example, motor and motors are running in parallel. Again, that is a coherent operation. That means a generator and motor running in parallel, that is called a non-coherent operation. Otherwise, it is a coherent operation. So, for a coherent operation, if you notice, the two machines having inertia constants, inertia constant H1 and what? H2. They are already on common base, careful. Then H equivalent can be written as H1 plus H2 if they are on common base. Okay, clear? And so for non-coherent operation, H equivalent will be H1 H2 by H1 plus H2. But what about M equivalent? M1 plus M2. But here M equivalent will be M1 M2 divided with M1 plus M2. So indirectly what you can understand here, so M equivalent is increasing here, but M equivalent is what? Decreasing here. Because of coherent operation, M equivalent is increasing. Non-coherent operation, M equivalent will decrease. So that's why if M equivalent increases, then what happened? Acceleration alpha decreases. Change in rotor angle with respect to time decreases and stability increases. If the rotor angle is changing very slowly with respect to time, then system is more stable. And here exactly opposite. Alpha increases, change in rotor angle with respect to time increases, and ultimately the stability of the power system, if you notice, that will decrease. Okay, so that's about the importance of coherent operation. Coherent operation will improve the system stability. But generally in power system we have coherent operation because we have n number of generators which are running in parallel. Next, power flowing through a transmission line under steady state. See, there is a transmission line, we have a sending end port and we have a receiving end port. We need to calculate what is the power flow at the receiving end. So PR is the receiving end power delivered, active power delivered, and QR is the receiving end reactive power delivered. Now Z is the series impedance of the line. We can write mod Z at an angle theta. What is mod Z? Under root of R square plus X square. And what is this theta? Tan inverse, I'm directly given here, VSVR by Z cos of delta minus theta. Okay, actually cos of theta minus delta. Anyway, both are same, cos of delta minus theta or theta minus delta. Okay, clear? Yeah. So, and VR square by Z into cos theta. Cos theta can be replaced there as R by Z from the impedance triangle. Okay, And similarly, the QR expression, Vs VR by mod z, sine of theta minus delta, VR square by z into sine theta. These are the two expressions which are very important. And condition for PR max. What is the condition for PR max? You need to differentiate the active power. To get the condition for PR max, we need to differentiate the active power with respect to delta and equate to 0. And if I do, I will get this delta equal to theta. So from that I can calculate PR max, and reactive power corresponds to PR max. But if you notice, the reactive power corresponds to PR max is negative. What is the meaning, sir? So when the transmission line is delivering, or a synchronous generator is delivering maximum active power to the load, means load power factor is leading. Okay, receiving end power factor is leading. So to deliver maximum active power, the synchronous machine is operating at leading power factor. Synchronous machine operating at leading power factor means it should be under excited. It should be under excited. Okay, clear? Because so load has to deliver the reactive power back to the generator. That means the generator is consuming the reactive power. That means it must be under excited. But think about in terms of power system for a transmission line. If you want to deliver maximum active power to the load, load must be capacitive. Load should be capable of supplying reactive power back to the line. But practically all our loads are induction motors. 85% of the loads are induction motors. So that's why to achieve this maximum active power delivery condition, we need a capacitive compensation at the receiving end, so that capacitor can supply what the load is required and what the line is required. This is what the line requirement. Similarly, we have a load requirement QL. So the reactive power capacity of that capacitor is line requirement plus load requirement. Line requirement is 10 MVAR and load requirement is 5 MVAR, and capacitor should supply 15 MVAR. That means without capacitor or without reactive power compensation at the receiving end, we cannot utilize the full capacity of our transmission line or full capacity of generator. So that's why the idea is the shunt capacitive compensation is preferred here to get maximum utilization of transmission line or maximum utilization of generator. So that is the thing you need to notice. And the next thing is if Vs equal to VR, and then you can substitute in PR max formula, we get this. And condition for maximum possible PR max. See, if you want to get a condition means, let's see, who are the variable here? Since the transmission line means Rx, which are in series, I can control the X by controlling what? Series compensation. But if you want to control the X, yes, you are using series compensation. So that means variable is X here. So you just differentiate PR max with respect to the reactance of the transmission line and equate to 0. And finally we get this condition X equal to root 3R. That means X bar ratio equal to what? Root 3. Mod Z equal to we get 2R and theta equal to 60 degrees. Correct or not? So, but X bar ratio root 3. But in a practical system, X bar ratio is very high, which is greater than 5. So that's why we need to decrease the X bar ratio. That means you have to decrease the value of X. If you want to decrease the value of X, the best way is let's use a series capacitive compensation. The series capacitive compensation we need to use here. With the help of series capacitive compensation, we can decrease the value of reactance. That means we can decrease the overall reactance value. Okay, this is XC external series capacitive reactance. With the help of that, I can achieve this condition. The idea is very simple. XL minus XC external by root 3, by R equal to root 3. We can do it. By using an external capacitor, we can achieve this. Right? Clear? And if that is the case, what is the PR max? V square by 4R, and QR corresponds to PR maximum is minus root 3 into V square by 4R. If you see, the power factor is 0.5 leading. Okay? Because we get tan inverse root 3. Tan inverse root 3 is nothing but what? 30 degrees. Cos 30 is 0.5. Okay, sorry, tan inverse root 3 is 60 degrees, cos 60 is 0.5. That means when transmission line is delivering maximum possible active power to the load and the load power factor is 0.5 leading. That you have to understand. Next, steady state stability, sir. See, steady state stability means it is the ability of the power system to remain in synchronism if the load on the machine is gradually increased. For example, if you have a generator and there is a load, you are just increasing this load. Okay, if I increase the load up to how much power the generator is remain in synchronism, that is called steady state stability limit. That means when the load is gradually increases, then what? So the generator, the stability will be slowly decreases. At one point the generator is at verge of stability. After that, even if there is a small increase in load, the generator lose synchronism. Okay, clear? And what is the steady state stability? It is the ability to maintain the generator or to maintain the system in synchronism or to regain the steady state after it has been subjected to a gradual increase in load. Okay, so we can calculate steady state stability limit as well. So steady state stability limit means it is a maximum power that can be delivered to the system. For example, if you take a generator, this is the equivalent circuit of the generator and this is the power angle equation, you know this. But what is the condition for PR max? You need to differentiate electrical power with respect to delta and equate to 0, and I will get delta is 90 degrees. That means for stability region, maximum possible delta is 90 degrees ideally. So what is P max? Indirectly EV by XX. Correct or not? If you want to substitute delta 90 degrees, we get P max, that is EV by XC. So from that we can write dou P by dou delta is EV by XS cos delta. P is what? EV by XS sin delta. EV by XS I can replace as P max. Dou P by dou delta and power angle equation. These two are very, very important. This dou P by dou delta is also called synchronizing power. Why? Because let's see, dou P by dou delta is 0 here. Here it is positive and here it is what? Negative. See, in this region, if there is an increase in load angle means there is an increase in electrical power. For increase in load angle means there is an increase in load, there should be an increase in electrical power. If load increases, electrical power decreases means that is an indication of instability. So till here, if load increases means load angle increases, electrical power increases. But here, if load increases, what happened in this region? Load increases, electrical power is decreasing. That's why system is unstable. That means up to 90 degree system is stable, and after 90 degree system is unstable. That means the dou P by dou delta is the slope of the power angle curve. Correct or not? The dou P by dou delta is what? Slope of this power angle curve. Slope of power angle curve. That explains what? Steady state stability. Correct or not? So dou P by dou delta explains the steady state stability, and dou P by dou delta is maximum at delta equal to 0. Okay, because if you notice dou P by dou delta equation, what is dou P by dou delta equation? P max cos delta. If you substitute delta equal to 0, then dou P by dou delta is maximum. Remember this, delta equal to 0 means dou P by dou delta is what? Maximum, but electrical power is 0. Delta 90 degrees, dou P by dou delta is what? 0, but P is what now? P max. Correct or not? Clear? Dou P by dou delta is 0, but P is what? P maximum when delta is 90 degrees. Okay, clear, sir? So that means at delta 0 degrees, dou P by dou delta is very high, system is more stable, but transferring 0 power. But if delta 90 degrees, system is what? Almost unstable, but transferring maximum power. So that means we must have a compromisation between dou P by dou delta and electrical power. The system must be stable and should supply what? Some power. Okay, that is the idea. Anyway, let's see, dou P by dou delta positive means delta 90 degrees stable system. Dou P by dou delta negative means what? Delta is greater than 90 degrees and it is an unstable system. If dou P by dou delta is 0 means delta equal to 90 degrees, marginally stable system. Okay, have a look here. Yeah, I told you just now, for delta 0, electrical power is what? This is electrical power, this is dou P by dou delta, also called synchronizing power coefficient. Okay, so if delta equal to 0 degrees, we get dou P by dou delta maximum, but electrical power is 0. So we get a best compromisation at delta equal to 45 degrees. That is why ideal limit of load angle is what? 90 degrees. But practical limit of load angle is always less than 45 degrees, generally less than 30 degrees, very close to 30 degrees. Okay, that is the practical limit of load angle for a synchronous machine. Okay, clear? And dou P by dou delta is also called synchronizing power coefficient. We already discussed that. Anyway, for salient pole machine, we have a xd greater than xq. This is the power angle equation for salient pole machine. EV by XD sine delta plus V square by 2 into 1 by XD minus 1 by XQ times sine 2 delta. So we can write C1 sine delta plus C2 sine 2 delta. I hope you understand what is C1, EV by XD, C2 V square by 2 into 1 by XD minus 1 by XQ. I think this is XQ, this is XD, careful. Yeah. Next, delta max is less than 90 degrees for salient pole machine. If you see here, this is what the plot for salient pole machine, power angle curve, delta versus P, power angle curve. This is a plot for cylindrical rotor machine, this is a salient pole machine. Exactly delta max is 90 degrees here, but here less than 90, that's what I written here. Delta max less than 90, salient pole machine, careful about this. Delta max equal to 90 for cylindrical rotor machine. And P max of salient pole machine is always greater than P max of cylindrical rotor machine for same power rating. Yeah, as we already discussed, dou P by dou delta is called synchronizing power coefficient. That is nothing but K, we say K, that is dou P by dou delta, P max cos delta. Synchronizing power also sometimes you asked to calculate. In synchronous machines also you might have done this calculation, K into delta delta. But careful, after calculating K, you must be substitute delta delta in radians. But basically we calculate this K for initial rotor angle. After that there is a disturbance, means what is the synchronizing power. That is explained by this formula. Next, steady state stability from swing equation. Okay, so how to calculate the steady state stability from swing equation? See, careful, when you are solving for swing equation, generally we neglect the damping, but very rare cases damping will be included. Okay, in GATE till now there is no question with damping, but it's an untapped area. Okay, but you must understand if the damping is given, what happens. Okay, so damping coefficient KD will be added here. This is a swing equation modified with the damping coefficient KD. If the swing equation is in megawatt, careful sir, the damping coefficient unit KD is nothing but damping coefficient. And what are the units of damping coefficient here? Megawatt seconds per electrical radians, otherwise megajoules per electrical radians, if the swing equation is in megawatt in actual form. If swing equation is in per unit form, and KD units are second square per seconds per electrical radians. Please notice that. Okay, clear, and that will help you in calculations. So we can calculate the damped frequency oscillations, and natural frequency of oscillations, damping factor and damping ratio. And we know that in control system, zeta equal to 1 critically damped, zeta 0 undamped, zeta greater than 1 over damped, and zeta less than 1 means it is a under damped case. Okay, so remember all these formulas. Okay, clear, till now there is no question on this formula. This is an untapped areas. Okay, so careful about this. Next, transient stability, sir. Transient stability deals with what? Large disturbances followed by a large disturbance. If the system is stable, means that is called a transient stable system, followed by a large disturbance. If the system is unable to recover its synchronism, means it is a transient instability. Okay, large disturbances means sudden change in load, faults on the power system. All this comes under large disturbances in power system. But what are the assumptions for transient stability? The first assumption is generators are modeled with transient reactance. But if you really notice, for generator operation, so we have a subtransient reactance, transient reactance, and steady state reactance. But generally the generator is modeled with transient reactance. That's what I am saying for transient stability analysis. And change in reactance of machine due to change in frequency during disturbance is neglected. See, I hope you understand this point. See, reactance formula is what now? 2 pi f into inductance. Inductance is generally a constant, but during disturbance the rotor speed of the synchronous machine will definitely change. If rotor speed changes, the frequency also changes, because frequency is directly proportional to rotor speed. If frequency changes, reactance also changes, but that change we are neglected. And effect of governor control is neglected. That means during disturbance the mechanical input to the generator is always assumed to be constant, but actually speaking governor will control that mechanical input, but we are assumed to be constant. But generally governor effect is what? Contributing for improving the stability. Similarly, effect of excitation control is also neglected. That means E is assumed to be constant. So here Pm is assumed to be constant. Damping of synchronous machine is neglected. Just now we discussed the damping coefficients Kd, that is equal to be 0. That means swing equation is what now? Md square delta by dt square, that is equal to simply Pa. Okay. And saturation of synchronous machine is neglected. That means synchronous reactance is always constant. Resistance is neglected for synchronous machine. Saliency is neglected. Saliency means what? Xd minus xq is called what? Saliency, that is equal to 0. That means even though it is a salient pole synchronous machine, what is the power angle equation? P max sin delta. Cylindrical rotor machine anyway, that is P max sin delta. Salient pole machine also better to consider what? P max sin delta, then only analysis is easy. Now what is the swing curve? See, followed by a large disturbance, we plot the swing curve. It is a curve between delta versus time. Okay, we are just plotting the variation of load angle with respect to time. Okay, so if you notice here, initially the rotor angle is delta naught. Followed by a large disturbance, the load angle is maybe increasing like this, and after that it starts decreasing. Then this is the new rotor angle or new settling angle delta 1. Now this is what? Delta 2, and similarly there exists what? A delta max. Now that delta max equal to 180 minus delta 1. The idea is very simple here. Initially rotor angle is delta naught, followed by a large disturbance. If rotor angle is increasing, then it start decreasing now. That's enough to conclude system is stable. Followed by a large disturbance, if the rotor angle is continuously increasing like this, and this is called unstable variation. Okay, now this is what? Stable variation. So the idea is very simple. Followed by a large disturbance, you just see the load angle variation. If load angle variation is continuously increasing till delta max, after that also increasing, that's enough. You can directly conclude that system is unstable. If load angle is coming up to delta max and then start decreasing, marginally stable. If the load angle is coming up to some delta 2 which is less than delta max, then what? Start decreasing means system is definitely, absolutely stable. So just see here, delta naught is pre-disturbance steady state rotor angle. Delta 1 is what? Post-disturbance steady state rotor angle if system is stable after the disturbance. Delta 2 is the maximum rotor angle or maximum excursion of rotor angle during oscillations or before settling to new steady state operating point. Okay, delta max just now we defined. And what is the importance of delta max? See, if the rotor angle increases and if it is increasing above delta max, then you can say system is unstable. Okay, so and slope of the swing curve is d delta by dt, sir. The slope of the curve, there exists a d delta by dt equal to 0 for a stable system. Here it is 0, but unstable system is d delta by dt is always positive. Okay, clear? That means from the slope of the power angle curve we can conclude steady state stability. From the slope of the swing curve, that is d delta by dt, we can conclude transient stability of the system. Clear? Now equal area criteria, sir. What the equal area criteria is saying? Followed by a large disturbance, if the area under the PA delta curve, PA d delta curve is 0 means, then that's enough to say system is stable. But careful, so when this is correct, acceleration area equal to deceleration area, then only the area under the PA delta curve, PA d delta curve is what? 0. Okay, clear? Understand? So, and first important thing is equal area criteria, if you notice, valid for single machine system, single machine infinite bus system. In short we say SMIB, and not valid for multi machine infinite bus system, but also valid for two machine system. In that case no infinite bus. Careful, it is not valid for multi machine infinite bus system, but it gives what? Absolute stability of the system. Okay, clear? Now there is a case study. The mechanical load on the motor is suddenly increased. See, this is what the initial mechanical load on the motor. Now mechanical load is suddenly increased from PM naught to PM. So but at point A initially the rotor is operating here with some rotor angle delta naught under steady state. So that's what I written. But suddenly at point A what happened? Mechanical load is increased from what PM naught to PM. That means electrical power is what here only, PE less than what PM. So rotor decelerates here. Why? Because mechanical load is more than electrical power. Then rotor speed is what? Equal to synchronous speed but decreasing trend. Load angle equal delta naught only but increasing trend. That means we are in forward swing. Correct or not? Then what I can say here, from A to B, since we are in forward swing from A to B, what happens A to B in this region? Mechanical power is more than what? Electrical power. Accelerating power is PE minus PM. Na? Since mechanical power is greater than electrical power, again what now? Rotor is what? Deceleration only, and rotor speed is here equal to synchronous but decreasing trend. But what happened here? Less than synchronous, but because of deceleration it is in what? Decreasing trend. And load angle is what? Greater than delta naught. Okay, this is not less than delta naught. Load angle is greater than delta naught but what? Increasing trend only. Okay, but at point B, mechanical power equal to electrical power and accelerating power is 0. Okay, at point B, rotor is neither accelerated nor decelerated. But careful, shall we settle here? No. Why? Because at this point rotor speed is what now? Decreasing and it is becoming what? Less than synchronous speed. Ultimately rotor speed is less than synchronous speed minimum here. Okay, because after that point rotor speed is what? It's going to increase. But load angle is what now here? Delta 1, but it is increasing trend. Why? Rotor speed less than synchronous speed means always load angle will increase. Okay, clear? Now after that from B to C what happens here? Electrical power is greater than mechanical power. Now the reverse operation, rotor speed what? Increasing trend but less than synchronous speed only. Suddenly it will not catch the synchronous speed. So load angle also increasing trend. Why? The rotor speed is less than synchronous speed. At point C, why I am assuming point C here? Because at this point rotor speed is recovered to synchronous speed. Why? Because here in the forward journey here rotor speed is less than synchronous speed and also what? Increasing trend. That's why it may catch the synchronous speed maybe at point here. Okay, so if the rotor speed is catched at synchronous speed but increasing trend only, why? Electrical power is greater than mechanical power. So load angle is what now? Delta, but load angle is constant, but a moment later it starts decrease because of rotor speed is going above synchronous speed. Why? Because rotor speed is increasing trend. If rotor speed is going above synchronous speed means what happened? Rotor speed greater than synchronous speed means load angle is decreasing. Motor action less than synchronous speed, load angle will increase. For motor action I am writing, sir. And if you notice later at C to B again, because earlier forward journey, now it's a backward journey. Again rotor speed is what now? Greater than synchronous speed but increasing trend. Load angle is decreasing at point B and again A to C, B to A and finally at A. So that means the rotor speed is here synchronous speed and here synchronous speed. And here in forward journey less than synchronous speed minimum, in backward journey greater than synchronous speed maximum. At point B I am talking. Okay, so with respect to time what happened? See, these 2 points are approaching to B and finally rotor speed at B will be synchronous speed. In the first swing, this, second swing it will come up to here, third swing, fourth swing, fifth swing, something like that, and finally at point B only machine will settle. Okay, so that's what the conclusions I written here. Have a look. During disturbance rotor is swinging from A to C and finally settling at what? B under steady state. That is the idea. At B it is settling under steady state. During forward swing, swinging from A to C, at A and C rotor speed is synchronous speed but at B rotor speed is less than synchronous speed and minimum. During backward swing, that is C to A, at A and C rotor speed is synchronous speed only but at B rotor speed is what? Greater than synchronous speed. If system is stable after disturbance, then under steady state at point B the rotor speed is recovered to synchronous speed and there is no concept of A and C under steady state. All these points are merged at what? B, A, C and going towards B. That is the idea. Okay, clear? Now basically transient stability calculations, sir. We have to calculate the stability of the system for a given increase in load, calculation of transient stability limit, calculation of maximum rotor angle, and by how much load suddenly increased without loss of synchronism, and critical clearing angle and critical clearing times. So these are the things we calculate from the transient stability analysis. Now quickly determining of the stability. The idea is what here? The load on the machine is earlier PM naught. Initially load is PM naught, now it is increased to what? PM. Then we have to comment on whether the system is stable or not. So to comment on system stability, let's see, this is what mechanical power and electrical power, and this area is called accelerating area, sorry, decelerating area. Mechanical power is greater than what? Electrical power. And this is what available deceleration area, that is called A2 dash, because we are going up to delta max. Delta max is 180 minus delta 1, where delta 1 is the new steady state rotor angle. So how to calculate that? PM equal to P max sine delta 1. From here we can calculate delta 1 value. Okay. Yeah. So after calculating delta 1, you can calculate these two areas, A1 and A2. After calculating A1 and A2 dash, if A2 dash is greater than A1, then system is stable. A2 dash is less than A1, system is unstable. A2 dash equal to A1, then system is marginally stable. That is how we can calculate. Next, calculation of transient stability limit. Remember sir, always it is 72.46% of steady state stability limit. That means P max. Okay, irrespective of whatever may be the given P max, this condition is always true. So what is transient stability, by the way? So if the load is increasing suddenly from 0 megawatt to PM megawatt, system is at verge of stability. System is at verge of stability means load angle delta 2 equal to what? Delta max, and rotor speed is recovered to synchronous speed exactly at what? Delta max. That's called verge of stability. That means A2 dash equal to what now? Exactly A1. Okay. Now the corresponding PM, this PM is nothing but transient stability limit. Okay. And you can calculate the delta 1, and from there I can calculate it. PTSL is 72.46% of steady state stability limit. And calculation of maximum excursion of load angle. See, to calculate the maximum excursion of load angle for a given load change, that means the question will be given like this. Initial load is 10 megawatt, now the load is increased by 30 megawatt, that means the new load become 40 megawatt. Then what is the maximum rotor angle achieved by the rotor, or maximum excursion of rotor angle is asking. To calculate that, again you need to equate area A1 and what? Area A2. So after equating area A1 and area A2, let's calculate delta 2. Now that is the final answer. Okay. And then by how much load suddenly increased without loss of synchronism? Okay, to calculate that, if the load is PM naught initially, maybe I am assuming that this much load I can suddenly increase it without loss of synchronism. Means what? So for increasing of that load, this area A1 and A2 dash become same. That means the rotor speed is recovered to synchronous speed exactly at delta max. That means delta 2 equal to delta max. So again equating A1 and A2 dash, let's calculate delta 1. Then PM also you can calculate, but answer is PM minus PM naught, because he is asking by how much load suddenly increase. That means this much load suddenly increase such that the rotor speed is recovered to synchronous speed exactly at delta max, and delta 2 equal to what now? Delta max, and system is marginally stable. So that's why this much load, the gap, whatever it is called, that is by how much load that is suddenly increased without loss of synchronism. Okay. And calculation of critical clearing angle and critical clearing time. Sir, so to do this, depending on the type of fault and location of the fault, we can do, sir. So, so these are the formulas which is written for the third case. If you notice, the fault is at the middle of the line. In that case, there exists a pre-fault maximum power transfer, post-fault maximum power transfer, and during fault maximum power transfer. This is what? Pre-fault, during, post-fault. Okay, clear? So based on that we have a formula, and also we can see what if the fault is very close to the bus bar and what if the fault is on the bus bar. But careful, if the fault is on the bus bar and very close to the bus bar, P max 2 is what? 0. Okay, clear? P max 2 exists only if the fault is at middle of the line. If the fault is very close to the bus bar, P max 2 is 0. Okay, if the fault is very close to the bus bar, for these two cases only TCR formula is valid. And what is the formula for that? 2H into delta CR minus delta naught by pi F and PM square root. Okay, but for third case, if the fault is at middle of the transmission line, for this case critical clearing angle is calculated using numerical integration techniques.